Hello there, and welcome to Science for Sleep, where curiosity settles in softly beside you, and big questions unfold gently enough to dream to. Tonight, we're drifting outward, past clouds, past stars, and into a question that's been floating in human thought for as long as we've had eyes to look up. Where does the universe end? Or perhaps more curiously, does it end at all? It's one of those questions that sounds simple when whispered in the dark, and yet it stretches farther than any telescope, farther than light itself can reach. Before we start this slow, cosmic journey, I'd love to know, where in the world are you listening from tonight? Maybe you're under city lights, with their orange glow dimming the stars just a little. Or maybe you're somewhere quiet where the Milky Way hangs across the sky like an old photograph. Wherever you are, you and I are sharing the same vast universe, and that already is a comforting thought. If you find this little voyage of calm and curiosity soothing, if it helps you unwind or makes the edges of your thoughts a bit softer, I'd be grateful if you gave the video a like or perhaps subscribed. It helps this small, sleepy corner of science reach others who might need a gentle pause too. So, let's begin. Take a breath, slow and easy. Let the day fall behind. Tonight, we'll wander toward the farthest horizon we can imagine, the edge, or maybe the endlessness of the universe itself. It's hard not to wonder about boundaries. Humans have always been creatures of edges. We map coastlines, climb the last peak, draw borders on paper, even if the wind erases them in the sand. There's something reassuring about knowing where things stop. The end of a road, the edge of a forest, the rim of a known world. But the universe doesn't make it easy for us. Look in any direction, and it just keeps going. There's no clear wall, no boundary line, no "here be dragons" sign hanging at the edge of existence. And yet, somehow we've managed to measure how far we can see. What does it mean really to say the universe ends? You might picture a kind of cosmic wall, something out there in the distance where space just stops. But that's not quite how the universe behaves. Space itself isn't like a room you can step out of, or an ocean you can sail off the edge of. It's more like the surface of a sphere, except in 3 dimensions instead of 2. There's no outer rim. You can keep moving forever and never find an edge. But before we get too deep into geometry, it helps to step back and ask what it is we're actually seeing when we look into space. Every time you lift your eyes to the night sky, you're looking into the past. Light doesn't move infinitely fast. It travels at a fixed speed, just under 300,000 kilometers per second. That sounds fast, and it is, but across cosmic distances it's surprisingly slow. The light from the sun takes about 8 minutes to reach us, from the nearest star over 4 years. From the edge of the observable universe, it's been travelling for more than 13 billion years, which means quite literally, we can't see the universe as it is right now. We can only see what it was. Imagine it this way. Every point of light in the sky is a time capsule, carrying information from a moment long gone. The farther away you look, the older the universe becomes. It's as if you're peering through layers of time stacked across the sky. Somewhere, out there in the deep distance, there's a limit. Not because the universe ends there, but because light hasn't had time to reach us from beyond it. That invisible boundary is what astronomers call the observable universe. But that phrase, observable universe, hides something subtle. It doesn't mean that's all there is. It just means that's all we can see. Beyond that sphere, space doesn't stop. It simply extends into a region forever hidden from us, its light too far away, its signals too delayed. If the universe is a stage, we're sitting in the centre of a vast glowing bubble, only able to see as far as light has had time to travel since everything began. Beyond that, the curtain is closed, not by choice, but by physics, and that's where the mystery begins to unfold. For most of human history, the night sky looked infinite, but simple. The stars were thought to be fixed on a celestial dome, a perfect sphere surrounding the Earth. When astronomers first measured the distances between stars, then galaxies, and then clusters of galaxies, that old image shattered. The universe wasn't a small room at all. It was an expanding space, still growing, still carrying light from farther and farther away. That expansion means that distant galaxies aren't just sitting in place. The space between us and them is stretching, and that stretch carries them away faster than their own motion ever could. Some are moving away so quickly that their light will never reach us, no matter how long we wait. It's a strange thought, isn't it? That we live in a universe where most of what exists will forever remain invisible. Not because it's hiding, but because the cosmos itself is growing faster than light can travel through it. The edge we see isn't the end. It's a limit of sight. A moving horizon, like watching the sea from the shore. You can see the water curve away, but you know the ocean continues far beyond. Scientists often use analogies to make this easier to picture. One of the simplest is the balloon analogy. Imagine the universe as the surface of an inflating balloon. Galaxies are dots drawn on that surface. As the balloon expands, the dots move apart, not because they're crawling over the surface, but because the surface itself is stretching. Now, notice something subtle. There's no center on the surface. Every point is moving away from every other point, and there's no edge either. You can travel around and around the balloon's surface forever and never find a border. The universe in 3 dimensions behaves in much the same way. Expansion happens everywhere at once, and the edge isn't a place you can reach. It's simply the limit of what light has had time to show you. If that sounds a bit dizzying, you're not alone. Even astronomers sometimes describe these concepts with a kind of quiet awe. Because the truth is, when we talk about the end of the universe, we're really talking about the end of what we can know, and that line between known and unknown isn't fixed, it's always moving. As light from farther regions finally arrives, our observable universe expands. Every day the cosmic horizon reaches a little farther out, showing us a bit more of the ancient universe. In a sense, the cosmos is still revealing itself, one photon at a time. There's something almost tender about that. The idea that the universe isn't static but in constant conversation with us. Its messages travel for billions of years, crossing unimaginable distances, and eventually land here, faint and worn, but still whispering their story. When you look through a telescope, you're not just observing distant stars. You're listening to echoes from the beginning of time. Each one tells you where the universe has been, and in its own way, hints at where it might go. When we first realized the universe was expanding, it changed everything. Before that, most scientists believed the cosmos was eternal and unchanging. Then Edwin Hubble looked through his telescope in the 1920s and noticed that distant galaxies were redshifted. Their light stretched to longer wavelengths, a sign that they were moving away. The farther the galaxy, the faster it receded. From that pattern, we learned that space itself was stretching, carrying galaxies along like raisins in rising bread dough. Follow that motion backward in time, and you reach a moment when everything was once closer together, hotter, denser, the moment we now call the Big Bang. But even the Big Bang isn't an edge in the way we normally imagine. It wasn't an explosion in space, it was an expansion of space itself. There was no outside for it to explode into. Every point in the universe was once condensed together, and every point has been moving apart ever since. Which means there's no centre, no outer shell, and no wall at the edge of everything. Just more space, unfolding, cooling, growing fainter with distance. Still, the word end lingers in the mind. Maybe it's not an end in space we're searching for, but an end in understanding. What lies beyond the horizon we can see? Could there be regions of the cosmos so distant that their galaxies, their stars, their light will never touch us? The answer, according to what we know, is yes. There are parts of the universe forever beyond our reach. They're not gone. They're simply separated by expansion so vast that even light, the fastest thing we know, can't bridge the distance. It's a horizon written not by geography, but by time. And here's where it becomes quietly beautiful. The universe doesn't end in a cliff or a boundary. but in a fade. The light grows redder, fainter, stretched by the expansion of space until it slips out of the visible spectrum entirely. Beyond that, there may be galaxies, perhaps entire structures larger than anything we've ever seen, but their light will never reach us. The universe continues, but our window closes. What we call the edge is really the edge of visibility. The farthest point light can have travelled since the Big Bang. That radius, at the moment, is about 46 billion light-years in every direction. So our observable universe is a sphere about 93 billion light-years across. Not because the universe itself is that size, but because that's how far the light has managed to come. Beyond that, we can only imagine. You might think of it as a kind of cosmic fog. We can see as far as light allows, but not beyond the haze. And in that unseen region may lie answers to questions we haven't yet learned to ask. Scientists suspect the universe beyond our horizon looks much the same, filled with galaxies and clusters, stars and dust, but we can't confirm it. The patterns we observe in cosmic background radiation, that faint afterglow of the Big Bang, suggest uniformity on the larger scales. But as for what lies truly beyond, we can only speculate. In a way, that limitation defines us. Every generation extends the boundary of the known universe a little farther. Each new telescope pushes back the veil by a fraction, capturing light that has been travelling for billions of years. The James Webb Space Telescope, for example, has peered deeper than any before it, revealing galaxies formed just a few 100 million years after the Big Bang. When we look at those faint smudges, we're not just seeing distant places. We're watching the universe as a child. The more we learn, the more the horizon shifts. It's a humbling reminder that the end is never really an end, only a pause in perception. What we know now will someday be replaced by deeper understanding, just as the boundaries of old maps once gave way to new continents. Perhaps the universe works the same way. Every discovery expands the world we live in, not by changing the cosmos, but by changing our vision of it. And as you listen to these words, perhaps you can picture it, a glowing bubble of sight, centered on you, expanding slowly outward as time moves forward. Somewhere, far beyond the edge of that sphere, new light is on its way, carrying stories from corners of the cosmos we can't yet see. They'll arrive someday, long after we're gone, long after new eyes and new minds have taken our place. The horizon of everything is always in motion, always just beyond reach, and maybe that's what makes it so captivating. Because what we can't yet see is not absence, it's possibility. The universe doesn't end where our vision stops. It keeps going, indifferent to our boundaries, generous in its vastness. Somewhere out there, beyond the last flicker of visible light, there are galaxies still forming, stars being born, light still beginning its journey toward us. The cosmos doesn't close off, it only waits. And so, as our exploration begins, we stand here, tiny, curious, awake beneath a ceiling of ancient light, wondering not just where the universe ends, but whether end is even the right word. Perhaps what we're really asking is how far understanding can reach before mystery takes over. Perhaps the horizon isn't a limit at all, but an invitation. It's a strange thing, isn't it? How a single question can open into something as vast as the universe itself. The moment we ask, where does it end? We're already wandering beyond what we can grasp. Most questions lead us toward an answer, but this one seems to lead us deeper into itself. The farther we follow it, the larger it becomes, like watching a coastline unfold the closer you sail. We set out looking for a boundary, and find instead an endless horizon that keeps moving away. The human mind doesn't like that kind of thing. We evolved to understand edges, borders, surfaces, and separations. We know where the field ends and the forest begins, where water meets land, where the air thins at the mountaintop. Our ancestors navigated by landmarks, drew circles around their settlements, built fences to mark safety from wilderness. boundaries gave structure to life. They defined here and there, inside and out. So when we lift our gaze and find no edge at all, no border in the sky, no line marking where everything stops, it unsettles something old inside us. You can feel it even in small ways. Think about how the night sky looks on a clear evening. There's comfort in its quiet repetition, the same constellations, the same steady planets, but beneath that calm lies a quiet disorientation. You realise for just a moment that there's no top or bottom to any of it. The stars don't hang in a dome. They surround you completely in all directions, stretching on without end. And even if you close your eyes, the thought of it remains vast and silent, pressing outward into your imagination. That feeling, the mixture of wonder and unease, is something every civilization has shared. The ancient Greeks imagined a finite cosmos, a perfect crystalline sphere surrounding the Earth, because infinity felt impossible. The stars were fixed, eternal light set into a celestial shell. Beyond it, they believed, lay a realm outside of space, unreachable, unknowable. The early Chinese skywatchers pictured the heavens as an inverted bowl, the earth beneath like a flat plain. In some ancient Indian traditions, the cosmos rested on an infinite ocean of potential, cycling endlessly through creation and dissolution. Each version tried to make the infinite human-sized. Each drew a shape around the unshapeable, to make existence feel less like an abyss and more like a room we could live in. But as our tools grew sharper and our curiosity braver, the walls began to crumble. The telescope replaced the naked eye, and suddenly the stars weren't fixed points but suns of their own, scattered across unimaginable distances. The Milky Way, once thought to be the entire universe, turned out to be one galaxy among billions. Every time we found an edge, it dissolved. It's an odd pattern in human discovery. The moment we think we've reached the end, it expands. Once the universe was the solar system, then it was the Milky Way. Then it became a web of galaxies stretching farther than light can travel in the age of the cosmos. Even now, scientists sometimes wonder if our universe is itself part of something larger, a multiverse, a grander structure beyond what our laws of physics can describe. Every answer creates more room for questions. There's something both humbling and strangely soothing about that. Because when you think about it, the question of the universe's end isn't really about outer space. It's about us. It's about the way we try to fit meaning into immensity. When we ask, where does it end? We're also asking, where do we fit? In a cosmos without borders, we look for something that feels like home, a centre, a direction, a scale that matches our senses. But the universe, in its quiet indifference, offers none of those things. It just is, vast and ongoing, expanding silently into regions we'll never touch. And yet, even knowing that, we keep asking. Perhaps because questions are how we orient ourselves. A sailor without a shore still has the horizon. A thinker without an answer still has the wondering. The question itself becomes a kind of anchor, a way of standing in infinity without being lost. When scientists talk about the limits of the universe, they often use words that sound deceptively simple. Finite, infinite, bounded, unbounded. But beneath those terms lies a thicket of meaning that can twist the mind. A finite universe isn't necessarily one with edges. It could curve back on itself like the surface of a sphere. If you travelled in a straight line through such a universe, you might eventually end up where you started, having never crossed an edge at all. Infinite space, by contrast, just keeps going, never looping, never closing. Both are mathematically possible. Both fit within our best theories of cosmology, and both feel equally impossible to imagine. It's remarkable that even with all our technology, radio telescopes, space observatories, satellites that measure cosmic radiation with extraordinary precision, we still don't know which one we live in. The observable universe, the bubble of space we can see, looks flat on the larger scales. But flat doesn't always mean infinite. It could simply mean so large that its curvature is too subtle to detect, like an immense planet that seems flat when you're standing on it. Our cosmic horizon is simply too small a window to reveal the true shape of the whole. So we're left in a peculiar position. We can describe what the universe is doing, expanding, cooling, forming galaxies, generating new stars. But not what, if anything, it's expanding into. Space itself is the thing stretching. There's no external backdrop, no room beyond the room. It's as though the universe is creating more of itself with every passing moment, each point of space carrying its own local expansion, everywhere at once. To ask what's outside is like asking what's north of the North Pole. The question itself starts to lose meaning, but it still stirs the imagination. Philosophers have always loved that tension between knowledge and mystery. Some describe it as the difference between the known universe and the unbounded whole, everything that might exist beyond our reach. Even if we never see it, the idea of it shapes how we think. Because if the universe truly has no end, then everything we are, everything we see, is just one small patch in an infinite mosaic. And if it does have an end, if it's finite but unbounded, then somewhere out there, the fabric of space may loop back, meaning every direction eventually leads home. Either way, we're living in a reality that refuses to sit still inside the lines we draw for it. There's an irony here too. The same expansion that hides the universe's edge from us is also what allows us to exist at all. In the early universe, matter and radiation were packed together so tightly that no stable structures could form. As space expanded and cooled, it created room for stars, galaxies, and eventually us. If the expansion had been slower, gravity might have pulled everything back into a dense mass. If it had been faster, matter might have spread too thin for anything to take shape. The very process that makes the horizon unreachable is also what makes the present moment possible. When cosmologists describe this expansion, they often talk about co-moving coordinates, a fancy way of saying that galaxies are carried along with the expansion, rather than flying through space like bullets. From our perspective, everything seems to be rushing away from everything else, but from each galaxy's point of view, it's at the centre of its own expanding bubble. There's no preferred centre, no special vantage point. Every observer in the universe sees roughly the same picture, which means that in some distant galaxy, there may be beings, if beings exist there, asking the very same question. Where does it end? It's a comforting thought, that curiosity itself might be universal, that the urge to look outward and wonder could be as natural to consciousness as gravity is to matter. We don't know if that's true, of course. We've never heard from anyone else. But the mathematics of the cosmos suggest that if life can arise here, it could arise elsewhere, under different skies, in different forms, perhaps with its own stories about where everything stops. Maybe somewhere out there, someone, or something, is staring into its own dark horizon, wondering the same things you are right now. And maybe that's the quiet answer to the question that stretches forever, that it isn't meant to be answered, it's meant to be shared. Across generations, across cultures, maybe even across galaxies someday, this question connects us. Not because it gives certainty, but because it reminds us of the scale of what we don't yet know. Every scientific discovery we've ever made has started with that kind of question. The kind that doesn't fit comfortably into language but keeps echoing in the mind until someone builds a tool big enough to chase it. When Galileo first turned his telescope to the sky, he wasn't trying to solve infinity, he just wanted to see more clearly. Yet that act, looking, pushed the edge of the known world outward. Each time we do it, the question stretches a little farther. There's something gentle about that process. Science isn't really about closing mysteries, it's about learning how to live with them more deeply. We name, measure, and model the universe not to cage it, but to listen to it. Each new theory is like another instrument added to an orchestra we're only beginning to hear. And even though we know our hearing will never catch every note, we listen anyway. Because wonder, like the universe itself, doesn't seem to have an end. Sometimes people ask scientists whether the universe having no end makes them feel small. It's a fair question. Standing beneath a sky full of ancient light can make you feel like a single breath in a vast silence, but smallness isn't the right word for it. Scale and significance aren't the same thing. You can be tiny and still be part of something infinite. In fact, being aware of that vastness is itself a kind of belonging. A galaxy doesn't need to know it's part of the cosmos, but you do. You can hold that thought in your mind. The awareness that you are a fragment of a story that reaches beyond visibility. That might be the most extraordinary thing the universe has produced. And so we keep asking. We build bigger telescopes, send probes farther, refine equations, and share late-night conversations about the edges of existence. Each time we do, the question stretches again, pulling us along with it, a little farther from certainty, a little closer to wonder. The universe, it seems, rewards curiosity not with final answers but with deeper questions. Maybe that's its way of keeping us moving, of ensuring that even in the face of endlessness we don't stop exploring. And as you lie there, maybe half awake, maybe already drifting, you can imagine that question itself as a kind of horizon. It doesn't end, it opens, it expands quietly, like the universe it describes. Somewhere in that expansion, between knowledge and mystery, between the seen and the unseen is where we live, curious, awake, listening. If there's one thing that defines the human story, it might be our strange habit of trying to see what can't be seen. We point our eyes, our instruments, and eventually our imaginations toward horizons that lie far beyond reach. Somewhere deep in our nature, there's a quiet refusal to stop looking. Even when the darkness seems complete, we keep searching for a glimmer. It's not just about curiosity, it's survival too. The more we see, the more we understand, and the better we can find our place within the vastness. But when it comes to the universe, sight is an imperfect guide. The cosmos doesn't reveal itself easily. It hides behind distance, time, dust, and laws of physics that twist light into strange paths. Seeing the unseeable, then, has become one of humanity's most delicate arts. For most of our history, the sky was a mystery we could only look at with the naked eye. The stars shimmered, the moon waxed and waned, and the occasional comet scratched a glowing line across the heavens. That was the full extent of our cosmic window. Everything beyond that was imagination, myth, and philosophy. The ancients built temples aligned with solstices and monuments that traced the movement of stars, not because they understood what those lights were, but because they wanted to feel connected to whatever lay beyond them. Their eyes saw points of light, but their minds saw patterns, stories, and gods. The night sky was both map and mirror, a reflection of how we made sense of the unknown. Then, 4 centuries ago, something changed. A craftsman's tool for looking at ships across the sea was turned toward the heavens. In that moment, the telescope transformed from glass and wood into an instrument of revelation. Galileo's simple tube of lenses showed that the moon wasn't a perfect smooth sphere, but a world marked by craters and shadows. It showed that Jupiter had moons of its own, tiny points of light circling a distant planet, proving that not everything revolved around the Earth. What had been invisible to all of human history became visible to one man standing on a balcony. And with that, the universe got bigger overnight. That was only the beginning. Over the centuries, we've built bigger and clearer eyes to pierce deeper into the dark. The first telescopes revealed planets and moons. Then came the discovery of galaxies, nebulae, and clusters so vast they made even our Milky Way seem modest. But every time we improved our instruments, we also found new kinds of invisibility. Space is full of things that don't give off light, or whose light is blocked, bent, or stretched beyond what our eyes can detect. To see them, we had to learn to look differently, to turn light itself into data. Modern astronomy doesn't rely on sight in the ordinary sense anymore. We see the universe by collecting signals, by turning invisible forms of radiation into images we can interpret. The night sky, if you could see it through all wavelengths, would be unrecognizable. Radio waves hum from the cold clouds between stars. Infrared light glows from dust that's invisible in optical wavelengths. Ultraviolet radiation pours out of newborn stars, while X-rays blaze from the violent hearts of galaxies. Even gamma rays, the universe's most energetic light, flicker from the deaths of massive stars and the surroundings of black holes. Every type of light tells a different part of the story, and together they form a cosmic symphony that spans the full range of the electromagnetic spectrum. One of the most extraordinary things about light is that it's both messenger and time capsule. When a telescope catches a photon from a distant galaxy, it's intercepting something that's been travelling across space for billions of years. That single particle of light has crossed expanding space, bent around galaxies, passed through dust and gas, and survived cosmic background radiation, all to end its journey in the mirror of an instrument on a small planet orbiting a modest star. When astronomers collect enough of those photons, they reconstruct an image not of what the universe looks like now, but of what it looked like long ago. Seeing, in cosmology, is a kind of time travel. The deeper you look, the older the light. To reach the edge of visibility, astronomers rely on an arsenal of telescopes, each designed to see a different kind of invisible. Radio telescopes, like the great dishes of the Very Large Array in New Mexico, listen for faint signals from gas clouds and distant galaxies. They can pick up whispers of hydrogen, the most common element in the universe, and trace how it forms stars across cosmic time. Infrared telescopes, such as the James Webb Space Telescope, look through the veils of dust that hide newborn stars in ancient galaxies. Dust that would block visible light becomes transparent at infrared wavelengths, allowing us to see regions of the universe that were previously dark. High above Earth's atmosphere, X-ray observatories like Chandra or NuStar reveal the violent side of the cosmos, exploding stars, colliding galaxies, and the glowing disks of gas spiraling into black holes. These are sights that no human eye could ever witness directly, yet they are among the most important clues to how the universe evolves. Together, these instruments form something like a multi-sensory perception of reality. We no longer look at the cosmos, we listen, feel, and translate it across frequencies. The universe has become something we don't just see, it's something we detect. But even with all those tools, there are regions we can't penetrate. Some things are invisible not because they're hidden behind dust, but because they simply don't interact with light at all. Dark matter, for instance, makes up most of the matter in the universe, yet it neither emits nor absorbs light. We know it exists only because of its gravity. Galaxies spin faster than they should based on the visible matter they contain, as if held together by an unseen web. Astronomers map that web indirectly, tracing its influence on the motion of galaxies and the bending of light. But dark matter itself remains unseen. The largest structure in the universe is something we can't look at, only infer. Beyond even that lies dark energy, the mysterious force that seems to be driving the accelerated expansion of the universe. Unlike dark matter, which pulls things together through gravity, dark energy pushes them apart. It's not an object or a field we can point to. It's an effect woven into the fabric of space itself. Trying to see dark energy is like trying to see the act of expansion itself. We only recognize it by watching distant galaxies drift farther apart than they should. It's another reminder that much of the universe doesn't just lie beyond sight. It lies beyond comprehension, at least for now. It's humbling to realize that even with our most powerful instruments, most of the cosmos is invisible. All the stars, planets, and galaxies that fill the night sky make up less than 5% of what exists. The rest is dark matter and dark energy, unseen, unfelt, unlit. We live surrounded by an ocean of invisibility, glimpsing only the foam at its surface, and yet, even with that limitation, we've managed to map a portion of the universe that spans tens of billions of light years. That's the quiet triumph of modern astronomy, seeing not with eyes, but with reason. There's a strange beauty in the way we convert faint traces into knowledge. A telescope doesn't capture an image the way a camera does. It collects photons, counts them, measures their wavelengths, and stores them as numbers. Those numbers are then processed, calibrated, and translated into images. The colorized pictures we see in magazines or on screens aren't literal snapshots. They're representations of data, carefully constructed to show what the human eye can't perceive. When you look at a photograph of a nebula glowing in blue and gold, you're not seeing true color in the ordinary sense. You're seeing a translation of information, wavelengths beyond human vision, mapped into something we can interpret. That's what makes modern astronomy such a fascinating blend of art and science. We turn the invisible into something visible, knowing that what we see is both real and constructed. The universe doesn't present itself to us. We assemble it from signals, much like how the brain builds the world from the flickers of the eyes. Seeing the unseeable is, in a sense, a collaboration between the cosmos and our curiosity. Of course, light itself has its limits. As we look farther out, the expansion of the universe stretches light waves, shifting them toward the red end of the spectrum. Eventually, the light becomes so stretched that it falls below the infrared range and into the microwave or radio bands. This process, called redshift, defines the boundary of what we can observe. Beyond a certain distance, light is stretched so thin by cosmic expansion that it never reaches us at all. There lies the ultimate invisibility, not because of dust or darkness, but because of the geometry of space-time itself. And yet, even that boundary has been probed. The faintest, oldest light we can detect comes from the cosmic microwave background, the afterglow of the Big Bang. It's not visible light, it's microwave radiation, the residue of a time when the universe was only about 380,000 years old. Before that era, the cosmos was too hot and dense for light to travel freely. Photons constantly bounced off charged particles trapped in a glowing fog. When the universe cooled enough for atoms to form, light was finally set free, and it's been travelling ever since. That ancient light now bathes the entire sky, stretched by expansion into microwaves, so cold it glows at just a few degrees above absolute zero. When we map that glow, we're seeing the universe at the earliest possible moment we can observe, the edge of the visible cosmos. It's hard not to feel awe at the idea that every bit of that faint radiation carries a story. The slight ripples in its temperature reveal the seeds of galaxies, the fingerprints of physics itself. From those tiny fluctuations, we've learned how the universe began, how it grew, and what it's made of. In the static between radio channels, in the cold hum of the sky, lies the oldest light in existence. That's the closest we can get to seeing the beginning. Still, the question lingers. What lies beyond that light? The answer, for now, is silence. No signal, no image, no data. Just the quiet acknowledgement that the universe continues in ways we cannot perceive. But that silence isn't empty. It's filled with potential, waiting for tools we haven't yet built. Every new generation of technology pushes back the darkness just a little more. The James Webb Space Telescope, with its golden mirror floating far from Earth, was designed to see the first galaxies that formed after that early glow. Already it's shown us structures older than we expected, brighter than our models predicted. Each image is a reminder that even the invisible is temporary, that with enough patience and ingenuity, we can turn mystery into understanding. And perhaps that's what it means to see the unseeable. Not just to look farther, but to accept that sight itself must evolve. The universe doesn't hide out of cruelty. It hides because its scale outpaces our senses. It's our task to keep extending those senses, to keep building instruments that can translate more of reality into view. The process is endless, but that's what makes it beautiful. There will always be another wavelength, another signal, another layer of light waiting to be found. Somewhere, even now, photons are racing toward us from regions we'll never name, their paths bent and stretched by gravity, their origins written in the language of the unknown. In a few billion years, their journey might end on the lens of some future telescope, and another generation will see what we cannot. The universe will continue unfolding its hidden chapters, one particle of light at a time, and as we follow that light, we come to understand something subtle, that seeing isn't only about vision, it's about connection. Every act of observation ties us, however faintly, to distant corners of the cosmos. Each image, each spectrum is a bridge between here and somewhere unimaginably far away. We might never reach those places, but their light reaches us, and in that meeting of photons and perception, the unseeable becomes seen, if only for a moment. From that fragile meeting of light and understanding, another question naturally begins to form. If we can only see so far, what truly defines the edge of sight? How do we measure the farthest boundary of a light itself? And what does it mean when even light, our most faithful messenger, cannot go farther? Light is a strange kind of traveller. It's fast, constant, and yet not infinite. It moves through the universe as both wave and particle, rippling and darting across the cosmos at a speed that seems absolute, the cosmic speed limit for everything that can carry information. About 300,000 kilometers every second, 8 minutes from the Sun to Earth, a little over a second from the Moon, and just over 4 years from the nearest star. Those numbers sound manageable until you scale them up to the universe itself. Then, that incredible speed begins to feel slow. The distances between galaxies are so vast that even light, racing tirelessly for billions of years, can't cross them before the universe itself changes shape beneath its path. The farther it goes, the more space expands, stretching its wavelength, dimming its colour, and pushing it into the infrared, then the microwave, until it fades into invisibility. That's where the edge of sight begins, not at a physical wall, but at the point where light can no longer keep up. When we talk about the universe's edge, what we usually mean is the edge of the observable universe. The farthest distance light has had time to travel since the beginning of everything. That distance isn't fixed, it's a moving frontier, constantly growing as more light reaches us from farther away. The current estimate places that boundary about 46 billion light-years in every direction. But the number itself hides something subtle. The light we see from those farthest reaches began its journey when the universe was only a few 100 million years old. The space it crossed has stretched dramatically since then, expanding the distance between us and the point where that light originated. In other words, the farthest light we can see comes from regions that are now far, far beyond 46 billion light-years away. The observable universe is not a snapshot of where things are, but of where they were, a time map wrapped around us like a glowing shell of history. That idea, that sight is bound by time, is one of the most profound consequences of light's finite speed. When you look at the moon, you're seeing it as it was a second ago, the Sun, 8 minutes ago, the nearest major galaxy, the Andromeda, about 2.5 million years ago. Every glance at the sky is a journey through layers of the past stacked by distance. The universe doesn't allow us to see it as it is, it only lets us see what it used to be. For scientists, this delay is not an inconvenience but a gift. It turns the universe into a natural time machine. Every distant galaxy is a record of an earlier era, frozen in the light that left it long ago. The farther away we look, the younger the universe appears. A nearby galaxy shows us the cosmos as it is now, mature, organised, filled with complex structures. A faint smudge at the edge of detectability shows us the universe as a child, smaller, hotter, more chaotic. By assembling these views, astronomers can trace the entire history of cosmic evolution, from the formation of the first stars to the sprawling web of galaxies that fill space today. But the speed of light does more than shape what we can see. It defines what's possible. In the framework of Einstein's relativity, no signal, object, or information can travel faster than light. That limit is woven into the fabric of space-time itself. It's not a rule we could ever break with better engines or clever tricks. It's a structural feature of the universe, a boundary between cause and effect. If something could move faster than light, it could in theory arrive before it left, unravelling the order of time. The cosmos avoids that paradox by setting light's speed as the maximum pace of reality. Everything that exists is connected by that limit. Every photon, every signal, every heartbeat travels through time at the same universal rhythm, defined by light. That might sound abstract, but it's deeply practical. When astronomers measure the distance to faraway galaxies, they're not really measuring space in the ordinary sense. They're measuring time, how long the light has been travelling. A galaxy 10 billion light-years away isn't just far. It's 10 billion years old in our view. And because the universe has been expanding all that time, the distance between us and that galaxy today is far greater than 10 billion light-years. Light's finite speed means that far away and long ago are the same thing. The edge of sight is the edge of history. It's worth pausing to imagine what it means that light has a speed limit. For centuries, people assumed light moved instantaneously. The ancient Greeks debated whether sight worked by rays streaming from the eyes or by something entering them. It wasn't until the 17th century that scientists began to realise light had a measurable speed. In 1676, Ole Rømer, a Danish astronomer, noticed that the timing of Jupiter's moons varied slightly depending on Earth's position in its orbit. When Earth was farther from Jupiter, the eclipses of those moons appeared delayed. The simplest explanation was that light took time to cross the extra distance. From those delays, Rømer estimated the speed of light to within about 25% of the modern value. A remarkable feat for the tools of his time. Over the next few centuries, others refined the measurement. In 1849, Hippolyte Fizeau used a toothed wheel and a beam of light to measure how long it took for light to travel to a distant mirror and back. A few years later, Léon Foucault improved on the design using rotating mirrors, bringing the estimate even closer to the correct value. When Einstein built his theory of relativity in the early 20th century, he placed light's speed not just at the centre of physics, but at the centre of reality itself. In his equations, the speed of light isn't just how fast light moves, it's the conversion factor between space and time. It's what stitches them together into space-time. Once you understand that, the universe's structure begins to make more sense. Imagine the cosmos as a vast, four-dimensional stage where time and space are inseparable. Every event, a star forming, a photon leaving a distant quasar, a person blinking, has coordinates in both space and time, but no event can influence another outside the boundary defined by light. Draw a sphere around any point, expanding at the speed of light, and everything inside that sphere can be connected. Everything outside remains forever out of reach. Those spheres are like bubbles of causality, growing and intersecting, defining who or what can ever interact. The edge of one bubble is the ultimate horizon for the observer inside it. In cosmology, we often visualize this through what's called the light cone, a diagram showing the paths that light can take through space-time. Your own light cone spreads outward from your present moment, touching everything you could ever reach in the future. Another cone, inverted, extends back into the past, containing everything that could have influenced you. Beyond those cones lies the unreachable, regions of space that exist but are forever disconnected from your timeline. The same concept applies to the universe as a whole. The cosmic light cone defines what we can observe and what we can never know, no matter how long we wait. This idea leads to a quiet but profound realization. There are parts of the universe that will never, in any sense, be part of our story. Their light will never reach us, their gravity will never affect us, their histories will never overlap with ours. They exist beyond the cosmic horizon, expanding away faster than light can bridge the gap. Even if the universe lasted forever, we would never see them. It's not because light slows down, but because space itself expands faster than light can cross it. That expansion doesn't violate Einstein's limit. The rule applies to motion through space, not to the stretching of space itself. You can think of it like this. Galaxies aren't racing through a static void. They're being carried apart by the growth of the void itself. The fabric of space-time stretches, and with it, the distances between all things increase. As those distances grow, light travelling across them is stretched too. Its wavelength lengthens, its energy drops, and its colour reddens. Over billions of years, that redshift transforms visible light into radio waves until the original signal fades beyond detection. That's the physical reason the universe has an edge of sight, not a wall, but a limit where light loses the race against expansion. This boundary isn't fixed, it changes as the universe ages. The observable universe today is much larger than it was billions of years ago, not because space has expanded faster than light, but because more time has passed for light to travel. Yet, at the same time, the accelerating expansion driven by dark energy means that many galaxies we can see now will eventually slip beyond reach. Their light will grow fainter and redder until it disappears entirely. In the far future, distant galaxies will vanish from view, one by one, leaving behind only the few bound to our local group. To observers living trillions of years from now, the universe will appear small and dark, and the evidence of its expansion will be gone. They will see a cosmos that seems static and eternal, unaware that once it was vast and full of light. That long view of time gives the present moment a particular poignancy. We live in an era when the universe is still transparent, when light from the distant past still reaches us. It's a fleeting window in cosmic history, the only period when beings like us can look outward and piece together the story of the whole. Before us, the universe was too opaque. After us, it will be too dark. That we exist now in this narrow slice of time is both coincidence and consequence. The stars that made us possible were born in an expanding universe. Their light still carries the memory of that process. The edge of sight is also the edge of meaning, drawn by the interplay of light, time, and existence. When you think about it, there's something almost intimate about the way light connects us to the universe. Every photon that enters your eye has travelled across impossible distances. Some come from nearby lamps or reflections, others from stars hundreds or thousands of light years away. A few might even be ancient cosmic rays, remnants of long-dead stars. The night sky isn't a flat image. It's a mosaic of histories, each pixel a different age, each ray a different origin. The stars you see tonight may already be gone, their light just finishing the last leg of an unimaginable journey. In that sense, light is memory. The cosmos records itself in radiation, in every wavelength and frequency. The faint microwave background records the birth of the first atoms. The infrared glow of distant galaxies records the first stars. The visible light of nearby galaxies records the present age. Together, these layers form a history written not in words but in wavelengths. And because light moves at a finite speed, that history can never be erased. Once a photon begins its journey, it carries its origin forever. This realization reshapes how we think about the universe's structure. There's no single moment that defines now everywhere. Relativity tells us that simultaneity depends on motion and position. What you call the present moment isn't the same as the present moment for someone in a distant galaxy. Their clocks run differently because of motion and gravity. Light's finite speed means communication between those two presents is always delayed. In that sense, the universe isn't synchronized. It's more like a collection of overlapping perspectives, each limited by light's reach. That limitation doesn't make the universe smaller, it makes it deeper. The horizon of sight isn't a prison, it's a record of connection. It shows how far the universe has allowed us to look, how much of itself it's revealed through light. Beyond that horizon, the cosmos continues, not in silence, but in wavelengths too stretched for our instruments. Maybe one day, new kinds of detectors will sense even those signals, extending our reach yet again. For now, the edge of sight remains the outermost boundary of our knowledge, the frontier where physics meets imagination. It's worth remembering that even the most precise measurements we make, distances, redshifts, luminosities, are ultimately acts of translation. We turn faint signals into meaning, brightness into distance, colour into age. The data that define our understanding of the universe are nothing more than patterns of light, interpreted through mathematics and calibration. Yet, through that fragile process, we've mapped billions of galaxies, measured the age of the cosmos, and traced its expansion from the Big Bang to now. All of that knowledge, every model and diagram, rests on light moving through the dark. The speed of light, then, is both the measure of our reach and the symbol of our limitation. It gives us the universe as it was, not as it is. But perhaps that's fitting. We're creatures of memory as much as perception. We live in the past light of the cosmos, surrounded by the echoes of its earliest moments. Every glance upward is a glimpse backward, every observation a reunion with the ancient. Somewhere beyond the edge of what we can see, new light is still being born. Photons from stars that will take billions of years to arrive. By the time they do, our sun will be gone, our planet cold, and whatever follows us will have its own ways of seeing. But those photons will still carry their stories, crossing space at that same unbreakable speed, racing toward whatever eyes or instruments might be waiting. The edge of sight will move outward again, and the universe will continue revealing itself, one beam at a time. When we look out into the universe, we aren't really looking outward. We're looking backward. Every star, every galaxy, every faint smudge of light we see in the deep sky is an echo from the past. The farther away we gaze, the older the light becomes, until eventually what reaches us isn't just ancient, it's primordial. In this way, telescopes are more than instruments. They're time machines. They don't transport us physically through time, but they allow us to witness time itself stretched across the sky, light preserved across billions of years, carrying with it a story that began before Earth even existed. That idea might sound like metaphor, but it's literal physics. Light doesn't age in the way we do. To a photon, time doesn't pass. It travels through space at the speed of light, and according to relativity, for anything moving at that speed, time stands still. From its own point of view, if it had one, a photon leaves its source and arrives at its destination instantly, no matter the distance. But from our slower human perspective, that same journey could take billions of years. So when you catch the faint light of a distant galaxy in your telescope, that light has been in motion for almost the entire history of the universe, crossing an ever-stretching space to reach you. It's a message from a time long before humans, before the Earth, even before the Milky Way was fully formed. We're used to thinking of time as something that moves forward, one second after another. But in the universe, time is revealed all at once, layered through space. The night sky is like a fossil record, not of bones or rocks, but of light. Close objects show the recent past. Distant ones reveal the deep past. To observe the cosmos is to peel back layers of time, each one farther and older than the last. When astronomers talk about looking at a galaxy 10 billion light-years away, they mean they're seeing that galaxy as it looked 10 billion years ago. The light began its journey when the universe was still young, when stars were just beginning to assemble the elements that would one day form worlds like ours. This layering of light means that the universe is, in a sense, both ancient and new, depending on where you look. In the same frame of the sky, you can see light that's a few minutes old, and light that's over 13 billion years old. A photon from a nearby star might have left when you were a child. a photon from a distant quasar might have left when there were no planets in our solar system. The universe gives us both the past and the present at once, stitched together in a tapestry that spans all of time. The most powerful telescopes ever built are designed not just to look far, but to look back. The James Webb Space Telescope, orbiting far from Earth in the quiet darkness beyond the moon, was created with this purpose in mind. Its golden mirrors are tuned to catch infrared light, the kind of light that's been stretched and cooled by billions of years of cosmic expansion. That's the light from the earliest galaxies, the first structures to form after the Big Bang. When Webb captures it, it's not seeing those galaxies as they are now, but as they were when the first stars were igniting, when the universe was only a few 100 million years old. In those faint, red-shifted glows, astronomers see the beginning of structure, the moment when matter stopped being evenly spread and started to clump, when the first stars forged the first heavy elements. It's like watching cosmic dawn in slow motion. There's a deep irony in that. The farther we look, the younger the universe becomes. But the act of seeing requires light, and light takes time to travel. So we can never see the universe as it is right now. We only see it as it was. The present universe, the true state of everything at this moment, is invisible to us, because the light from its farthest regions hasn't arrived yet. That means the cosmos we know, the one mapped by all our telescopes and theories, is a kind of ghost, a luminous memory of how things used to be. It's not that the universe is hiding from us. It's that the very structure of space-time keeps us forever one step behind. The speed of light, which sets the pace of cause and effect, also sets the rhythm of knowledge. Every observation is delayed by the time it takes for light to cross the distance between what is and what can be known. The farther you look, the older the truth becomes. We exist within that delay, surrounded by a shell of information that grows with time but never catches up to the present. In that sense, every telescope is a time traveller, not because it breaks the laws of physics, but because it uses those laws to their fullest. The mirrors, sensors, and instruments we build are really devices for decoding the past, translating ancient photons into maps, spectra, and images. The more sensitive they are, the farther back we can go. The faintest signal carries the most ancient story. It's remarkable how much we've learned from this backward vision. By studying light from distant galaxies, astronomers have reconstructed nearly the entire history of the cosmos. They've traced how hydrogen and helium, the simplest elements formed in the Big Bang, gave birth to stars that fused heavier elements in their cores. They've measured how galaxies grew from tiny irregular clumps into grand spirals and elliptical clusters. They've observed the expansion of space itself, stretching the light from those early times into the long wavelengths we see today. All of that from nothing more than faint ancient light. Sometimes, when scientists describe the universe in this way, they sound almost like archaeologists. But instead of digging into soil, they dig into space. Each photon is a shard of evidence, each wavelength a clue. By collecting enough of them, we reconstruct epochs that no longer exist. The early universe, with its glowing hydrogen fog and violent starbursts, is gone forever. Yet its light remains, still crossing the void, still carrying its pattern of heat and density. When that light arrives, it becomes data, and from that data, we recover the shape of time itself. You might wonder how far this cosmic archaeology can go. If we keep building better telescopes, could we eventually see the very beginning, the moment of creation itself? The answer, as it often is in cosmology, is both yes and no. We can see very close to the beginning, but not all the way. Beyond a certain point, the universe becomes opaque. Before about 380,000 years after the Big Bang, the cosmos was so hot and dense that light couldn't travel freely. Photons constantly scattered off charged particles, trapped in a brilliant plasma. The universe at that time was glowing, but it was a fog, not a transparent space. Only when it cooled enough for electrons and protons to form neutral atoms did light break free. That moment, called recombination, is the earliest visible surface of the cosmos, and its afterglow still surrounds us as the cosmic microwave background. That faint radiation, stretched by billions of years of expansion, fills every corner of the sky. It's the oldest light we can ever see, the farthest backward we can ever look. Beyond it, light itself is hidden, locked in a time before transparency. To go farther, we have to use other messengers, not light, but neutrinos or gravitational waves, ripples in space-time itself. Those too are time machines of a kind, though their signals are far harder to detect. One day, with more sensitive instruments, we might capture the whisper of the universe before light, the imprint of creation itself encoded in the waves of space-time. For now, the microwave background is our horizon, the oldest photograph the universe has allowed us to take. Looking at that ancient light is an exercise in humility. What it shows isn't a collection of stars or galaxies, but a nearly uniform glow, smooth to one part in 100,000. The tiny fluctuations, barely perceptible, are the seeds of everything that would later form. Those slightly denser regions would attract matter, grow into galaxies, and eventually into stars, planets, and life. Every cluster of galaxies, every sun, every thought and heartbeat traces back to those faint ripples in the earliest light. To look at them is to see the blueprint of existence itself. It's strange to think that a creature made of atoms living on a small planet billions of years later can look back and read that blueprint. The light has travelled for almost the entire history of the universe, only to end its journey inside a human-built sensor. When scientists measure the patterns of that light, they're not just studying physics. They're participating in a conversation that began at the dawn of time. The universe, through light, tells us where it's been. We, through observation, tell the universe that we're listening. Even now, new technologies are turning that listening into something more profound. Gravitational wave detectors, for instance, can sense distortions in space-time caused by massive cosmic events. Colliding black holes, merging neutron stars. Those waves, like light, carry information across the universe, but they're not blocked by dust or gas. They can travel through matter as easily as light passes through air. In time, they might reveal the earliest moments of the cosmos, when space itself rang with the vibrations of its own birth. In that sense, the universe is not silent. It hums, and every new instrument we build brings us closer to hearing that hum in full. This ability to observe the past raises a quiet, philosophical question. When we see light that's billions of years old, are we witnessing something that still exists or something that's gone? Many of the stars whose light fills our night sky have already burned out. Their photons continue on, carrying their image long after the source has vanished. The universe is full of such ghosts, signals from things that no longer are. In a way, everything we see is a kind of memory, preserved in light, persisting after its moment has ended. The cosmos remembers itself through radiation, and we, by observing it, become part of that memory. If you've ever stared at a deep field image, one of those photographs where a telescope stares at a tiny, apparently empty patch of sky for days or weeks, you've seen this in action. What looks like nothing reveals thousands of galaxies, each a swarm of billions of stars. Some are so distant that their light began its journey when the first multicellular life was forming on Earth. Some left when the universe was only a few % of its current age. You can look at that image and know that almost everything in it has already changed. Many of those galaxies have merged, evolved, or faded, yet in that frozen light they remain, forever young. That's the power of cosmic time machines. They don't just show us what's out there, they remind us what out there means. Distance isn't just space, it's duration. Every point of light is a slice of the past, and when you look across the night sky, you're seeing billions of those slices at once. The result isn't a single moment, but a panorama of all moments, layered and luminous. It's as if the universe was showing you its own memory, unfolding across the darkness, whispering the long story of itself in waves of light. There's a quiet irony to all this. The deeper we look, the younger the cosmos appears, until at the limit we find the beginning, a smooth, glowing field of potential. Yet as we look inward, into our own existence, we find the opposite: complexity, awareness, reflection. The universe has aged, and in doing so, it has grown the capacity to observe itself. When we look out, we're looking at our own origin. When we understand that light, we're understanding the process that made us possible. In that sense, the telescope isn't just a machine for seeing, it's a way for the cosmos to remember itself through us. The universe keeps time in light. Every star records its age in colour. Every galaxy carries its history in the way it spins. Every photon tells how far it has travelled. The sky, if you could read it fluently, would be a timeline written in wavelengths. We're just learning to read that language, slowly, carefully, one observation at a time. And as we do, the line between seeing and remembering begins to blur. The farther we look, the deeper we move into memory, until the entire universe becomes an archive of its own becoming. When you think about space, it's easy to imagine it as an empty background, a vast silent container in which galaxies float, like islands in a still sea. For centuries, that's how most people pictured the universe, a static stage where the actors were stars and planets, all held in place by invisible forces. But the truth, as we've slowly discovered, is stranger and more alive. Space isn't a void we exist inside of. It's a fabric, dynamic, elastic, and constantly changing. The universe doesn't just contain motion, it is motion. And what we call the expansion of the universe is really the stretching of that very fabric itself. That idea is one of the most revolutionary in science, and yet it's also one of the hardest to picture. When we say the universe is expanding, it's tempting to imagine galaxies flying outward through pre-existing emptiness, like shrapnel from an explosion. But that's not what's happening. The galaxies aren't moving through space. The space between them is growing. Every distance is increasing, not because the objects themselves are rushing outward, but because the coordinate system, the grid of reality, is stretching. To understand it, imagine drawing dots on the surface of a balloon. As you inflate the balloon, the dots move farther apart, even though they're not moving along the surface. The surface itself is stretching, and that's what increases the distances. From any dot's perspective, all the others seem to be moving away, and the farther they are, the faster they appear to recede. But there's no centre on the surface. Every point is equally valid. The same is true of our universe. Every galaxy sees every other galaxy moving away, and each observer feels as though they are at the centre of expansion. This concept was first realised in the early 20th century, when astronomers began to notice a pattern in the light of distant galaxies. Their light was shifted toward the red end of the spectrum, a sign that they were moving away from us. The farther away a galaxy was, the greater the redshift. Edwin Hubble plotted those distances against their velocities and discovered a linear relationship. Galaxies recede in proportion to how far they are. The simplest explanation was that space itself is expanding uniformly. That discovery transformed cosmology. It meant that the universe wasn't static, as people had long assumed. It was dynamic, evolving, changing, and growing. But the discovery raised an immediate question. Expanding into what? If the universe is everything, what lies outside it for it to expand into? The answer, as strange as it sounds, is nothing. Not empty space, not another dimension, simply nothing at all. The universe doesn't expand into a larger container. The metric that defines distance between points is what changes. Space doesn't need an outside to grow, any more than a balloon surface needs a third dimension for its circumference to increase. Expansion happens within the structure itself. It's an unsettling thought at first because it challenges the way we think about size and motion. We're used to movement being relative to something else, a car moving along a road, a planet orbiting a star. But cosmic expansion isn't motion through space, it's motion of space. The galaxies aren't travelling anywhere, they're being carried apart by the growth of the universe's fabric. To make sense of this, physicists developed what's called the metric expansion of space, the mathematical description of how distances change as the universe evolves. The framework comes from general relativity, Einstein's theory that gravity is not a force acting at a distance, but a curvature of space-time caused by energy and mass. According to that theory, the geometry of the universe is shaped by its contents. Where there's matter or energy, space curves. On the larger scales, that curvature defines how the universe expands. Einstein's equations allow many possible cosmic shapes, depending on how much matter and energy the universe contains. If there's enough mass, gravity slows expansion and can even reverse it, leading to a future collapse, a big crunch. If there's too little, expansion continues forever, thinning matter out until galaxies drift apart beyond visibility, a big freeze. The exact balance between those fates depends on the density of the universe. For decades, scientists debated whether we lived in a closed universe that would eventually contract, an open one that would expand forever, or a perfectly flat one balanced on the knife edge between the two. Measurements over the past few decades suggest that the universe is very close to flat, but its expansion isn't slowing down, it's speeding up. That discovery came at the end of the 20th century, when astronomers studying distant supernovae found they were dimmer than expected, implying they were farther away than they should have been if expansion was slowing. The simplest explanation was that some unknown form of energy, now called dark energy, is driving the acceleration. The universe isn't just expanding, it's expanding faster and faster, as though pushed by a pressure intrinsic to space itself. Dark energy remains one of the greatest mysteries in science. We don't know what it is, only that it makes up about 70% of the universe's total energy content. It might be a property of the vacuum, the energy of empty space itself, or it could be something more exotic, like a field that changes over time. Whatever it is, it's not just filling the universe, it's shaping its destiny. As space expands, more of it comes into existence, and with it, more dark energy. The effect compounds, driving galaxies apart faster the farther they are. That's why, in the distant future, only the nearest galaxies will remain visible. Everything else will recede beyond the cosmic horizon, their light stretch beyond detectability. The picture this paints is both beautiful and melancholy. We live in a universe that is both connected and self-separating. Everything began in one dense, hot state, a single region smaller than an atom, and has been expanding ever since. That expansion gave rise to all structure, galaxies, stars, planets, and life. But it also ensures that given enough time, those structures will drift apart, isolated by the growing distances between them. The same process that brings creation also guarantees solitude. If you could see the universe from outside, though there is no outside, you would see something like a vast glowing foam, clusters of galaxies connected by filaments of dark matter, separated by enormous voids. Over time, the filaments stretch thinner and the voids widen. The cosmic web itself slowly fades as light from distant regions redshifts into darkness. On local scales, gravity still holds things together. Galaxies remain bound, stars orbit their centres, planets circle their suns. But on the grander scales, everything drifts. The universe doesn't grow like a fire spreading into new territory. It grows like a fabric being woven, its threads lengthening between all that exists. The expansion also affects how we perceive time. because the rate of expansion depends on the density of energy and matter. The early universe expanded differently than it does now. In its first fractions of a second, it underwent a burst of exponential growth known as inflation. That period, driven by a field similar to dark energy, stretched space faster than light could travel, smoothing out irregularities and setting the stage for everything that followed. When inflation ended, the universe continued to expand, but more slowly, cooling enough for matter to form. The radiation from that time is still visible today as the cosmic microwave background, the afterglow of that early heat. In that sense, expansion is more than just a feature of the universe, it's its defining rhythm. Space and time themselves are expanding, carrying everything with them, and that expansion isn't something happening out there, it's happening right here too. The distances between atoms don't change because local forces like electromagnetism and gravity hold them together, but the underlying metric that defines distance everywhere still evolves. If you could somehow switch off all binding forces, everything would drift apart with the expansion. Even now, in the empty spaces between galaxy clusters, space stretches quietly, unnoticed. It's difficult to feel this in any visceral way because expansion happens on scales far beyond human perception. The rate of increase is tiny on local distances, about 70 kilometers per second per megaparsec, meaning two galaxies a million parsecs apart, roughly 3.26 million light-years, move away from each other at 70 kilometers per second. On the scale of human life, that's negligible, but multiply it across billions of light-years, and the effect becomes cosmic. Distant galaxies recede so fast that their light is stretched by factors of hundreds or thousands, turning visible wavelengths into microwaves. In some ways, the expansion of space redefines what distance even means. Because light takes time to travel, the distance to a galaxy depends on what you're measuring, how far the light has travelled, how far away the galaxy was when the light left, or how far away it is now after billions of years of expansion. These can all be vastly different numbers. A galaxy whose light has travelled 13 billion years might now be over 30 billion light-years away. The space between us has grown while the light was in transit. That's why cosmological distances are so unintuitive. The universe isn't a static map, it's a process. There's also a quieter implication hidden in this expansion, that the universe doesn't have an edge in the traditional sense. If it's infinite now, it's always been infinite, just stretched thinner. If it's finite but unbounded, like the surface of a sphere, you could travel endlessly without finding a wall. The expansion doesn't add new stuff at the edges, it scales everything everywhere. The boundaries we imagine exist only in our attempts to visualize what infinity looks like. Sometimes people ask what causes the universe to expand. What pushes it? The answer is subtle. Nothing pushes. Expansion isn't caused by an external force, but by the conditions set by the universe's own energy and geometry. In general relativity, empty space isn't passive. It has energy, and that energy affects its curvature. The equations show that a universe filled with matter and radiation naturally evolves over time, either expanding or contracting depending on the balance of energy and gravity. The universe we inhabit happens to be one where expansion won. It's not hard to see the poetic weight of that fact, though I'll avoid turning it into poetry. The universe grows not because something tells it to, but because that's what its laws require. Expansion is not the result of motion, but of existence itself. The same physics that bends light, that holds planets in orbit, that shapes atoms. Those same rules stretch space across all of creation, and that expansion is steady, patient, beyond any force we could ever touch. When you look at the night sky, the stars seem still, fixed in patterns we recognize. Yet on cosmic scales, everything is moving. The galaxies drift apart, the clusters spread, and the fabric of the universe continues to stretch, millimeter by millimeter, light year by light year. If you could speed up time enough, you'd see it like a living thing, the great web of galaxies slowly thinning as distances grow, until only local clusters remain like embers cooling after a fire. That future isn't something to fear, it's simply the natural continuation of a process that's been unfolding since the beginning. The universe doesn't expand toward emptiness, it expands into possibility. Each increase in distance creates new paths for light, new configurations for matter, new ways for energy to move. It's the geometry of creation in motion, and perhaps that's what makes this discovery so profound. When scientists first realized that galaxies were receding, it meant the universe had a beginning, that it was once smaller, denser, and hotter. The expansion we see today is the lingering echo of that origin. The redshift of light is the record of time stretching itself. Every photon that reaches us carries evidence of that continual growth. The cosmos, in its vast silence, has been breathing out for nearly 14 billion years. As you lie there thinking about it, maybe it helps to imagine space not as a cold emptiness, but as a living structure, elastic, connected, always in motion. Galaxies are not dots floating in isolation. They're part of a grand web suspended within this expanding framework. The distances between them grow, but the pattern persists. The same laws that shaped the early universe are shaping it still, invisible but consistent. And as the expansion carries light farther and fainter, it brings us closer to another question. If the universe stretches endlessly, what happens beyond the regions we can see? How do we describe the parts of the cosmos forever hidden beyond our horizon? And what does it mean that the universe has a limit of observability, even though space itself may have no end at all? Beyond the farthest light we can see, there lies a silence we cannot break. Not the silence of empty space, but the silence of the unreachable, a region where the universe continues, but forever beyond our sight. This is what scientists call the cosmic horizon, the ultimate boundary between what can be known and what forever remains hidden. It isn't a wall or a border, it's a limit drawn by time, distance, and the unyielding pace of light. To understand where it lies and what it means, we have to follow light itself to the edge of its possible journey. Every beam of light that reaches us today began somewhere. A star, a galaxy, a quasar, a burst of energy from a collision in the early universe. Each photon carries the story of its origin. But no matter where it starts, that light must travel through expanding space to get here. And as space stretches, the distance grows. Eventually, the universe's expansion outpaces even light's ability to cross it. That's the horizon, the point beyond which light can never bridge the gap. Anything farther than that is part of the universe, but not part of our observable one. It helps to picture the observable universe as a bubble. We're at the centre, not because we're special, but because from every vantage point the universe looks the same. The edge of that bubble marks the distance light has been able to travel since the Big Bang, about 46 billion light years in every direction. Everything inside that sphere is connected to us by light. Everything beyond it is forever beyond reach. But that edge is not fixed. As time passes, new light arrives from regions once hidden, and the bubble grows. The universe reveals itself gradually, like an ocean slowly pulling back its tide, exposing more of the shore. And yet, even as we see more, we lose more. Because the universe's expansion is accelerating, there are galaxies we can see now whose light will never reach us again. The space between us grows faster than the photons can travel. It's as if we're standing on a shoreline watching ships sail away. Not because they're moving faster, but because the sea itself is widening beneath them. Those galaxies will fade from view, their light stretched into invisibility. One day, their last photons will arrive, and then there will be nothing. They'll still exist, still move, still shine, but in a realm cut off from ours by the growth of space itself. This horizon, then, is not a fixed border, but a moving one. expanding in some ways, retreating in others. There are actually two kinds of horizons to think about. The first is the particle horizon, the distance that light has travelled since the beginning of the universe. It marks the outer edge of the observable cosmos, the farthest light that's had time to reach us. The second is the event horizon, the distance beyond which light emitted now will never reach us in the future, no matter how long we wait. The two horizons are not the same. One shows us how far back we can see, the other shows us how far forward we can connect. Together they define the bubble of our cosmic awareness. When cosmologists map these horizons, they aren't guessing. They calculate them using the known laws of physics, the speed of light, and the rate of cosmic expansion. The result is both precise and profound. The observable universe contains roughly 2 trillion galaxies, each with billions of stars. That's just the portion within our light cone. Beyond that, the numbers explode into the unimaginable. The universe could be hundreds, thousands, or even infinitely times larger than what we can observe. We'll never know for sure. The light from those regions will never reach us, not even given infinite time. The expansion of space outpaces the transmission of information itself. Beyond our horizon, reality continues, unseen, unmeasurable, untouched. There's a quiet truth hidden in that. We often think of knowledge as something that can grow without limit, that if we build better tools and wait long enough, we'll eventually understand everything. But the universe doesn't work that way. It comes with a built-in limit. No matter how powerful our telescopes become, no matter how long we wait, there's a horizon that will never yield. It's not a temporary boundary caused by ignorance. It's a permanent feature of space-time. The universe has edges of knowability. There are places and times whose light will never touch us, not because we aren't clever enough, but because the geometry of existence forbids it. That might sound cold or fatalistic, but there's another way to look at it. The horizon isn't a failure of perception. It's a reflection of how deeply connected we are to the structure of the universe. The same physics that gives us stars and atoms and life also gives us limits. Those limits shape everything we know. If the speed of light were infinite, there would be no time, no causality, no sequence of events. Everything would happen at once. The horizon gives shape to reality by ensuring that information takes time to travel, that cause precedes effect, that history has meaning. Without those delays, the universe wouldn't be a story unfolding. It would be a single, motionless instant. Still, it's hard not to wonder what lies beyond that boundary. Theories give us glimpses, though not pictures. The simplest assumption, supported by all evidence so far, is that the universe beyond our horizon looks much like the universe within it. The same laws, the same patterns, the same vast web of galaxies stretching endlessly. The cosmic microwave background, that ancient afterglow from the Big Bang, shows us that on the larger scales the universe is remarkably uniform. No direction is special. That symmetry suggests that what we can't see probably continues in the same way, but there are other possibilities hinted at by mathematics and imagination. Some theories suggest that our observable universe might be one bubble among many, a region of space-time that inflated out of a larger multiverse. In that view, beyond our horizon could lie other bubbles, each with its own laws of physics, its own versions of reality. Some might be utterly empty, others might be filled with matter and energy unlike anything we know. We can't test those ideas directly, but they offer a kind of framework for thinking about the infinite, a way to give shape to the unknowable. The idea of multiple universes is easy to romanticize, but even without it, the reality is vast enough to stretch the mind. Consider that the light we see from the most distant galaxies began its journey when the universe was less than 1/10 of its current age. Those galaxies have been moving away ever since, carried by the expansion of space. By now, they're so far that any new light they emit will never reach us. They've crossed the event horizon, vanishing not with a sudden disappearance, but with a gradual dimming. The farther the light travels, the more it's stretched by expansion, until it fades into the background glow of the universe itself. It's tempting to think of the horizon as a kind of edge of existence, but that's not quite right. Space doesn't end there. The universe continues indefinitely, just unseen. Imagine standing on a vast plain surrounded by fog. You can see a certain distance in every direction. Beyond that, everything fades into grey. The fog doesn't mark the end of the world, it marks the end of vision. The cosmic horizon is like that. A fog of time and distance, not of matter. The landscape beyond it is real, even if we'll never walk there. This raises an odd but fascinating point. Every observer, everywhere in the universe, has their own horizon. The bubble of the observable universe is centered not on Earth, not even on our galaxy, but on each point in space. Someone living in a galaxy billions of light years away would see their own horizon centered on them, containing regions we can't see, just as we see regions they cannot. Every point in the universe is the center of its own observable sphere, and no two are the same. The cosmos is full of overlapping horizons, each a unique window into time. The result is a universe without a single center, but filled with centers everywhere, each one a perspective on infinity. In a way, that's a kind of equality. There's no privileged viewpoint, no cosmic throne. Every observer sees themselves at the heart of what they can know, surrounded by the vastness of what they cannot. The horizon defines not just the edge of visibility, but the edge of perspective itself. It's the line where knowledge ends and imagination begins. Even though we can't see beyond the horizon, we can still feel its influence. The distribution of galaxies we observe, the temperature of the cosmic background radiation, the way space curves, all these carry imprints of conditions that extend beyond our view. The universe we see is shaped by the universe we can't. In that sense, the invisible majority still leaves its mark. What lies beyond might be unreachable, but it isn't irrelevant. It determines how the observable universe behaves, how it expands, how it will evolve. We may not be able to see it, but it defines the context of everything we do see. That understanding comes with a kind of humility. We like to think of ourselves as explorers who can, given enough time, uncover every secret. But the cosmic horizon reminds us that mystery is a permanent part of existence. There will always be more universe than we can know. That's not a limitation to overcome, it's a truth to live with. It gives depth to the act of observation. To look at the sky is to acknowledge not just what's visible, but what lies beyond visibility. When you stare into the night, you're seeing only a small fraction of the total universe. The rest, the unobservable part, is vastly larger, perhaps infinitely so. Yet that fraction contains enough to fill every lifetime of curiosity. Every discovery, every photon caught by a telescope comes from within that narrow window, and even within it, there are distances so great that light from the most distant galaxies arrives faint and stretched, almost lost in the cosmic background. Each photon is a survivor, a messenger from a realm nearly gone from our reach. Astronomers often talk about the cosmic horizon not as a tragedy, but as a horizon of wonder, because even though it sets a limit, it also defines the edge of discovery. Every new telescope, every improvement in technology, pushes that line outward a little farther. The James Webb Space Telescope, for instance, has already extended our view into spooks we'd only theorized about, showing galaxies forming earlier, faster and brighter than expected. It hasn't broken the horizon, but it's made the boundary clearer, more meaningful. Every new glimpse adds another piece to the story of how the visible meets the invisible, and perhaps that's what keeps us looking. The knowledge that there will always be more to know, that there will always be an edge we can't quite reach, gives science its endlessness. The cosmic horizon isn't a discouragement, it's an invitation, a soft boundary that says, look as far as you can and then imagine farther. It's the promise that there's always something beyond, even if we can never touch it. When cosmologists calculate the ultimate fate of the universe, that horizon plays a crucial role. If expansion continues to accelerate, more and more regions will slip beyond our ability to see or affect. In the distant future, each gravitationally bound cluster of galaxies will become an isolated island, cut off from all others by the widening sea of space. Communication, travel, even awareness between regions will end. The horizon will close in around each island until, for all practical purposes, each cluster becomes its own miniature universe, unaware of the rest. That image of isolation growing from connection is haunting in a quiet way, but it's not entirely bleak, because even if the universe drifts apart, the laws that govern it remain the same physics that shaped the first atoms, the same constants that allow light to move and gravity to pull will continue. The pattern persists even as the picture changes. The horizon doesn't erase meaning, it simply redefines it. So when you think of the edge of the universe, try not to imagine an end. Imagine a boundary of vision, a limit to light. Beyond it, the universe continues, unbothered by our inability to see it. Somewhere out there, more galaxies form, more stars ignite, more light begins journeys that will never reach us. And in that, there's a quiet kind of comfort. The knowledge that creation doesn't depend on observation, that existence isn't diminished by invisibility. Even though we'll never see beyond that horizon, we can still understand it. We can measure how it grows, predict how it shifts, describe its geometry with equations that match observation with extraordinary precision. The unseen can still be known, not through direct sight, but through inference and reason. In that sense, the cosmic horizon isn't the end of science. It's its purest form, knowledge built on the recognition of limits. And as that limit fades into the unseen, another question begins to emerge from the dark, a question about shape. If the universe has no edge, then what is its form? If it extends endlessly, what geometry allows that? And if it bends back on itself, could we, in some way, return to where we began? When we try to imagine the universe, we often picture it as endless, a boundless black expanse speckled with stars. But when scientists talk about its shape, they mean something subtler. They're not asking how the universe looks from the outside, because there is no outside. They're asking about the geometry of space itself. Is it flat or curved? Does it stretch infinitely in all directions? Or does it wrap around on itself like the surface of a sphere? What happens if you travel far enough in one direction? Do you keep going forever? Or do you somehow end up where you started? These questions sound simple, but they go to the heart of what the universe actually is. To understand what shape means on a cosmic scale, you have to imagine geometry not as something drawn on paper, but as something woven into the fabric of reality. Einstein's general theory of relativity tells us that space and time aren't passive backgrounds. They bend and stretch in response to energy and mass. When you put matter in space, it curves. That curvature isn't a force acting from outside. It's the geometry itself changing. Gravity isn't a pull between objects. It's the motion of matter along the curves of space-time. The same principle that makes planets orbit stars also governs how the entire universe bends under the weight of all its contents. So when cosmologists talk about the shape of the universe, they're talking about its overall curvature, the way the geometry of space behaves on the largest scales imaginable. There are three main possibilities. The universe could be flat, closed, or open. Each corresponds to a different kind of geometry, and each one tells a different story about the cosmos's past and future. A flat universe means that space, on average, follows the rules of Euclidean geometry, the kind you learned in school. Parallel lines never meet. triangles add up to 180 degrees, and the geometry doesn't curve in any direction. In a flat cosmos, you could, in theory, travel in a straight line forever and never return to where you started. Space stretches endlessly, and its expansion continues without wrapping back on itself. A closed universe is curved like the surface of a sphere. It's finite but unbounded, meaning it has no edges, yet it loops back on itself. On the surface of Earth, you can keep walking in one direction indefinitely and eventually arrive where you began. The same could be true in three-dimensional space. If the universe were closed, a beam of light travelling far enough might someday circle around and return from the opposite direction. An open universe is curved the other way, like a saddle. In this geometry, space expands forever, but it does so with negative curvature. Parallel lines diverge, and the sum of a triangle's angles is less than 180 degrees. It's infinite and unbounded, but it has a different geometry than flat space. A geometry that stretches outward, never looping, never closing. For decades, scientists tried to determine which of these shapes described our universe. It wasn't just a question of aesthetics, it was a question of destiny. The shape of the universe depends on its total density of matter and energy. If there's enough mass, gravity pulls inward, curving space into a closed form. If there's too little, expansion dominates, and the universe opens forever. If it's balanced precisely between the two, the universe remains flat. In the middle of the 20th century, this became one of cosmology's central mysteries. Observations of galaxies and clusters suggested that visible matter wasn't nearly enough to close the universe, but there was also evidence of unseen mass, what we now call dark matter, and perhaps even other forms of energy that could tip the balance. The discovery of the cosmic microwave background in 1965 provided a new tool for testing these ideas. That faint afterglow of the Big Bang carries an imprint of the universe's shape. When scientists measured tiny fluctuations in that background radiation, they found that the scale of those patterns depended on how space bends. In a closed universe, light paths converge, making distant features appear larger than they would in flat space. In an open universe, light paths diverge, making them appear smaller. In flat space, the angles remain just right. By measuring those angles across the sky, cosmologists could test the geometry of everything. The results were astonishing. The data showed that, within a very small margin of error, the universe is flat. The pattern of the cosmic microwave background fits the geometry of Euclidean space almost perfectly. That means the total density of matter and energy in the cosmos is very close to a critical value, the precise amount needed to balance expansion and gravity. Not too little, not too much. A universe delicately poised between open and closed, expanding forever but never curving back on itself. That discovery, confirmed by multiple missions like WMAP and Planck, reshaped cosmology. It suggested that we live in a universe that is flat to within a fraction of a percent, at least as far as we can measure. But flat doesn't mean simple. On local scales, space is full of curvature. The warps and dips around stars, black holes and galaxies. What flatness means is that, when averaged over vast distances, those curves cancel out. The overall geometry is balanced, smooth, and large beyond comprehension. Flatness raises a new question, though. Why? The universe didn't have to start this way. In fact, if it were slightly different in its early conditions, even by a tiny fraction, it would have diverged dramatically over time. A universe just a bit denser would have collapsed long ago. One slightly less dense would have thinned into emptiness. The balance we see now is so precise that it seems almost improbable. The answer may lie in the first moments after the Big Bang. During inflation, the universe expanded exponentially, stretching space so rapidly that any initial curvature was flattened out, just as the surface of a balloon becomes flatter the more it inflates. Inflation took whatever geometry existed at the beginning and magnified it until, on observable scales, it became indistinguishable from flat. That's why our universe appears so delicately balanced. It's the residual shape of something that was once much smaller, blown up to cosmic proportions. Still, even if the universe is flat overall, that doesn't mean it's infinite. It could be both flat and finite if it loops back on itself in complex ways. Imagine a video game where walking off one edge of the screen makes you reappear on the opposite side. You'd never find a boundary, but the space would still be limited. Some cosmologists have explored similar topologies for the universe, models where space connects back on itself through multidimensional loops. In such a universe, light travelling far enough could, in principle, return from the other side. The entire cosmos could be a vast, self-connected manifold, seamless and edge-free. We don't know yet if that's true. Yet, so far there's no evidence of repeated patterns in the cosmic background, no sign that light is wrapping around. But the possibility remains open, especially if the universe is larger than our observable patch. Beyond our horizon, the geometry could bend in ways we can't detect. We see only a tiny part of the total, like a person on an immense plane who can't tell whether the ground is truly flat or gently curved. The question of shape also touches something more profound, the relationship between geometry and destiny. In a closed universe, expansion might someday halt and reverse, leading to a cosmic collapse. In an open or flat one dominated by dark energy, expansion continues forever. That means time itself has a shape, not just space. The geometry of the universe tells us not only where we are, but where we're going. And yet, even with these grand distinctions, it's worth remembering how smooth the universe is. On the larger scales, it's almost uniform, the same density, the same temperature, the same laws everywhere. But beneath that calm, the structure is intricate. Galaxies gather into clusters, clusters connect into filaments, and vast voids stretch between them. The shape of space provides the framework, but the matter within it paints the texture. If you could see the entire cosmos at once, you'd see a web of light and darkness, luminous threads of galaxies woven through invisible strands of dark matter. That web is the fingerprint of gravity operating within the geometry of space. The fact that the universe has a shape at all means it has rules, measurable, describable, and astonishingly consistent. Those rules allow us to trace the curvature of space not by touching it, but by observing how light travels. When light passes near a massive object, it bends. That bending, called gravitational lensing, is a direct consequence of curved space. By measuring how galaxies distort the light of those behind them, astronomers can map the invisible contours of gravity itself. On smaller scales, that lensing reveals the distribution of dark matter. On larger ones, it traces the shape of the entire cosmic web. In a way, light becomes our ruler and the universe our map. Sometimes, when scientists describe this, it sounds almost poetic, but underneath the calm explanations lies something deeply human. The desire to know the universe's shape isn't about curiosity alone, it's about belonging. To know the form of the cosmos is to know the stage we live on. Are we inside something finite, turning in endless loops, or are we adrift in an infinity with no walls? Both answers inspire awe, but in different ways. If the universe is infinite, then every direction extends without end. There's no center, no boundary, just a seamless continuation. That infinity, though impossible to visualize, carries a kind of comfort. It means there's always more, that existence has no limit. If the universe is finite, curved back upon itself, then everything connects. There are no edges, no outside, no void beyond, only a grand circle, closed and complete. Either way, the shape suggests wholeness, but perhaps what matters most isn't the geometry itself, but what it implies about our place in it. On human scales, the universe's curvature is imperceptible. The ground feels flat, the stars seem fixed, the distance is incomprehensibly large. Yet, All of it, the straight lines, the arcs, the spirals of galaxies, follows from the same geometry that shapes time. The equations that describe this are elegant but indifferent. They simply state that space bends, that time stretches, that everything moves according to those rules. The wonder is that such abstraction can explain everything we see. When you step outside at night and look at the sky, you're seeing a tiny patch of this grand structure. The constellations are local features, small imperfections in a geometry too vast to grasp. Yet they're also proof of connection. Every photon you see follows a geodesic, the straightest possible path through curved spacetime. That means each one has traced the shape of the universe on its way to your eyes. The night sky is a projection of geometry, the visible evidence of curvature made manifest as light. It's strange to think that the universe's shape might be something we can describe but never truly perceive. We'll never stand outside it to see its curve. We can only infer it from within through the behaviour of light and matter. But maybe that's fitting. We're part of the fabric we're trying to measure. Our own atoms curve space. Our own mass participates in gravity. The shape we study is also the shape that shapes us. As we continue to map and measure, we refine the details. The tiny deviations, the subtle twists in the cosmic background, the slight bending of light around clusters. Each piece brings us closer to understanding the universe's architecture. But even if one day we describe its curvature perfectly, that won't be the end of the story. Because knowing the shape doesn't tell us why it exists. Geometry gives structure, but not purpose. And beyond the smoothness of the cosmos lies another question. Not of form, but of extent. If the universe is flat and perhaps infinite, then how do we define its limits? How can something go on forever, yet still have a measurable age, a beginning in time? If you stare at the night sky long enough, there's a question that starts to linger. Soft at first, then heavier the more you think about it. Does it ever end? The darkness seems bottomless, the stars too many to count, the spaces between them too vast to measure. We know the universe began with the Big Bang, a single, expanding moment that gave rise to everything we see. But when we look outward, there's no sign of a boundary. The galaxies fade, the light stretches, the data thins, but nowhere is there a wall. So, is the universe infinite, stretching endlessly in all directions? Or is it finite, somehow contained? Perhaps looping back on itself in a cosmic circle with no edges to find. That question isn't just philosophical, it's one of the deepest in cosmology, because it defines not only how big the universe is, but how it works, how it began, how it will evolve, and what everything truly means. To decide whether the universe is infinite or finite, we first have to understand what those words mean in the language of physics. Infinite doesn't just mean large, it means without bound. No edge, no limit, no place where space stops. Finite doesn't necessarily mean small. It means measurable, enclosed, possibly curved in such a way that it connects back to itself. You could travel forever in one direction and eventually return to your starting point, never hitting a barrier, never finding an outside. It's important to remember that infinity is not a number. It's a concept, one that sits uneasily in science. In mathematics, infinities can be handled with equations and limits. In physics, they're trickier. Whenever infinities appear in our models, infinite density, infinite curvature, infinite energy, it usually means the theory has reached the edge of its usefulness. Reality tends to resist infinity. The universe might be vast beyond imagination, but actual infinity might belong more to thought than to nature. Still, the possibility can't be dismissed. The observable universe, the part we can see, has a measurable size, a sphere about 93 billion light-years across. But that's only the portion whose light has reached us since the Big Bang. There could be vastly more beyond it, perhaps infinitely more. The light from those regions simply hasn't had time to arrive. In that case, what we call the universe, is really just a visible patch of a much larger whole. To us it looks finite because our view is bounded by time. To the universe itself there may be no boundary at all. The current evidence suggests the cosmos is very close to flat as far as geometry goes. That alone hints strongly toward infinity. In a truly flat universe, space extends endlessly in all directions, but flatness doesn't prove infinity, it only suggests it. Space could be flat and still finite if it wraps round in the right way, forming a kind of multi-dimensional torus, a shape like a donut, where moving straight eventually brings you back to where you started. From inside it would appear endless, yet it would have a finite volume. That's one of the strange ways the universe can be both infinite to perception and finite in structure. Astronomers have tried to test whether we live in such a looping universe by searching for repeated patterns in the cosmic microwave background. If light circled the cosmos and returned from different directions, we might see matching patches of temperature variations, cosmic fingerprints echoing across the sky. So far, none have been found. The background appears smooth, unique, and unmirrored. That means if the universe does wrap around, the scale of that loop is much larger than the part we can observe. For all practical purposes, it might as well be infinite. There's also a practical way to think about the question. Suppose you could travel faster than light, ignoring all the laws of physics for a moment, and head straight in one direction. If the universe were finite and curved back on itself, you'd eventually return to your starting point. If it were infinite, you'd never return. You'd move through an endless expanse of stars, galaxies, and eventually darkness so deep that even starlight fades. The strange part is that both scenarios are possible under the same physical laws. The difference lies not in what's possible, but in how space itself is connected. To visualize that connection, it helps to think about the balloon analogy again. Not the surface itself this time, but the space within it. The surface of the balloon is two-dimensional and finite, yet unbounded. There's no edge. If you travel along it, you never find an end, but you can still measure its total area. Now imagine the three-dimensional version of that. Our universe could be the three-dimensional surface of a higher dimensional sphere, finite but without a boundary. The difficulty is that we can't step outside to see that curvature. We can only infer it from within, by measuring how light and matter move. So far, those measurements show no sign of closure. Every observation of the cosmic background, every survey of galaxies, points to a universe so large and smooth that any curvature is too subtle to detect. If it does curve, the radius of that curvature is enormous, far beyond the reach of our instruments. That's why, for now, most cosmologists treat the universe as effectively infinite. Not because we've proven it is, but because there's no evidence it isn't. The difference between enormous and infinite might be academic, but it changes how we think about everything. If the universe is infinite, it raises fascinating questions about repetition. In an infinite space governed by the same physical laws, every possible configuration of matter could occur somewhere, not once, but infinitely many times. That means there could be other regions, unimaginably distant, where the atoms arrange themselves in the same pattern as here. Somewhere, far beyond the horizon, there could be another Earth, another version of you listening to this same idea. The notion sounds fanciful, but mathematically, it follows from the logic of infinity. If the universe is truly endless and not random, then repetition becomes inevitable. The cosmos would contain not just variety, but echoes, every possible combination played out infinitely across the expanse. Of course, we'll never confirm that. Those hypothetical repetitions, if they exist, lie beyond any possible observation. The horizon of light defines a permanent separation between what's accessible and what's not. That's one of the quiet ironies of cosmology. The deeper we look, the more we realize that the most interesting answers lie just out of reach. Infinity isn't just a question of space. It's a condition of knowledge. If, on the other hand, the universe is finite, it carries its own kind of elegance. A finite universe could still be unimaginably large, billions of light years across, but it would have a total volume, a countable number of galaxies, a measurable amount of matter and energy. It would be self-contained, a structure that loops without edges. Some physicists find that idea more satisfying. Infinity, after all, is hard to reconcile with the finite age of the universe. The cosmos has existed for roughly 13.8 billion years. How can something that began in time be infinite in space? The answer might lie in the nature of the Big Bang itself. When people picture the Big Bang, they often imagine an explosion expanding into emptiness. But it wasn't an explosion in space. It was the expansion of space itself. Every point in the universe was once compressed into a smaller region, not a single point in pre-existing nothingness. That means the Big Bang didn't happen somewhere. It happened everywhere. The entire universe, whether finite or infinite, expanded together. If it was infinite then, it's infinite now. If it was finite, it remains finite, though vastly larger. The expansion scales everything equally. The shape doesn't change, only the size does. So even the beginning doesn't settle the debate. Both infinite and finite models fit the evidence. Inflation, the rapid expansion in the universe's first moments, tends to make any region appear flat and homogeneous, erasing traces of curvature. It could have inflated a finite universe beyond our ability to measure, or it could have produced an infinite one from the start. Either way, the observable patch we live in looks the same. That's why cosmologists often say the question may be unanswerable, not because it's meaningless, but because the distinction may be permanently hidden behind the limits of observation. Yet, even if we can't know for sure, the question itself teaches us something about perspective. When we talk about infinity, we're really talking about scale. The difference between what we can experience and what exists beyond experience. Our senses evolved for small things. The distance to a tree, the time it takes for the sun to set. The human brain can barely grasp the span of a galaxy, let alone an unending cosmos. So when we use words like infinite, we're stretching the limits of thought itself. We're describing something that can't be seen or measured, only reasoned toward. That act of reasoning is, in a way, its own kind of exploration. Infinity might be unreachable, but it's not unimaginable. Mathematics allows us to describe it, to map it symbolically, to build models that extend beyond what we can ever touch. Those models help us make sense of what's visible, even if the whole remains hidden. The universe doesn't need to be infinite for infinity to matter. It only needs to be large enough that for us the difference doesn't make sense anymore. It's possible that the cosmos is so vast that calling it infinite is simply more convenient. From our perspective, there's no practical difference between immeasurable and infinite. We could travel at the speed of light for the lifetime of stars and still not reach the edge. We could build telescopes 1,000 times more powerful and still not see a boundary. If we can never find an end, then for all purposes that matter to us, the universe is infinite. And yet, the idea of a finite universe carries its own quiet beauty. It suggests completeness, a cosmos that folds back on itself, where every direction eventually leads home. In such a universe, nothing is truly isolated. Everything is part of one continuous whole. The galaxies we see would be connected to themselves across vast unseen arcs of space. Light would wander forever, looping endlessly through the same cosmic structure. It would be a universe without edges, yet self-contained, eternal in motion but finite in volume. When you think about it long enough, the distinction between infinite and finite begins to blur. Both imply a universe without walls. Both defy our intuition about beginnings and ends. The difference lies in subtle mathematics, not in experience. Whether space goes on forever or eventually loops back, from where we stand it feels the same. Boundless, unreachable, endlessly expanding. The night sky gives no hint which is true. It offers only light fading into distance, and distance fading into darkness. Perhaps that's why the question keeps returning. Infinity has always haunted human thought. Ancient philosophers argued over whether the world could be infinite, whether the stars stretched forever or circled within a crystal dome. Even now, with satellites and computers and precision data, we're still asking the same question. The tools have changed, but the wonder hasn't. We still stand beneath the same open sky, looking into the same dark, asking how far it goes. What makes the question so powerful isn't the answer, but what it reveals about us. We seem drawn to boundaries, to finding where things stop. We map coastlines, name continents, count stars, as if knowing the edges gives shape to our own existence. But the universe resists that. It offers no clear border, no final coordinate. Whether infinite or finite, it's too large for ownership. It reminds us that we live inside something that doesn't depend on our understanding. It exists whether we measure it or not. So, maybe the point isn't to decide between infinite or finite, but to learn how to think in a world where both possibilities coexist. In one, everything continues forever. In the other, everything connects back. In both, we find no true edge, only the continuity of existence. The universe is whole, whether endless or enclosed. Its nature doesn't need our certainty, it only needs our attention. And as we keep observing, measuring, and thinking, the line between those two possibilities becomes more delicate. The more we know, the more we see that both are reflections of the same truth, that we live inside something vast, coherent, and self-consistent. The difference between infinite and finite may not matter as much as what it means to live inside such a system at all, to be a part of something so large that even the concept of outside no longer makes sense. In that realization lies something quietly transformative. If the universe is infinite, then we are part of an unending continuum. If it's finite, we are part of a complete whole. Either way, there's no border between us and the rest of existence. The atoms in your body are part of the same geometry that shapes galaxies. The expansion that carries the stars apart also stretches through the empty spaces between your molecules. Infinity isn't somewhere else. It's here too, written into the same laws that govern everything. As the galaxies drift apart, as space stretches and the horizons grow, the question of infinity remains not as a riddle to solve, but as a reminder of scale. It tells us how small we are, and how extraordinary it is that something so small can even ask. The universe might be infinite, but our awareness is finite, and somehow the two meet. Thought reaching out into endlessness, endlessness reflecting back through thought. If you were to step outside on a clear night and look upward, you might feel that the sky is some kind of dome. The stars hang overhead, scattered across a black surface that seems to curve around you. It's an old instinct, one that's been with humanity since we first began to look up. We sense enclosure even when none exists. Our eyes and minds crave boundaries. They need edges to rest on, places where things stop. But the universe does not offer them easily. The deeper we look, the more it refuses to end. The illusion of edges is one of the oldest tricks of perception, and perhaps one of the most beautiful. It's easy to see why this illusion feels natural. Everything in daily life has limits. A room has walls, a horizon has an end, an ocean meets a shore. Our sense of space evolved in a world defined by containment. To survive, we had to know where things stopped, where the ground dropped away, where the forest ended, where night began. Our senses and language were built for edges, so when we try to grasp a universe without them, something in our minds pushes back. We imagine borders even when the evidence dissolves them. For most of human history, people believed the universe had a literal edge. Ancient civilizations imagined the heavens as a dome, the earth as a disk, the stars fixed to a crystalline sphere. Even when the geometry changed, When the Earth became a sphere, when the Sun took the centre, the idea of an enclosed cosmos remained. There had to be a limit somewhere, a wall of stars, a boundary of ether, a point beyond which space simply stopped. Infinity was too unsettling to imagine. It wasn't until the 20th century that we truly began to accept a universe without boundaries. Einstein's equations and the observations that followed forced us to see space and time as continuous, connected, flexible, and without walls. Yet even now, the mind resists. When we say the universe is expanding, people often ask, expanding into what? When we say it has no centre, they ask, where did it begin? These are the ghosts of our instinct for edges, echoes of a way of seeing that no longer fits the scale of reality. The truth is that space doesn't need an outside to expand, and the universe doesn't need an edge to be whole. Expansion happens everywhere at once. Every galaxy moves away from every other, not because they're rushing towards some outer boundary, but because the distances themselves grow. There is no centre of the universe because the universe is not expanding into something larger. The expansion is the increase of space itself, and it happens everywhere equally. The illusion of an edge comes from trying to imagine the infinite using the mental tools of the finite. If you picture the surface of Earth, you can see the problem clearly. To someone walking across a plain, the world seems flat, and the horizon looks like an edge. It appears as if there's a place where the land stops and the sky begins, but when you reach it, the horizon has only moved farther away. It's not a real border. It's a perspective, a limit of sight. The universe is similar. The observable horizon isn't a physical barrier, it's just the distance light has been able to travel since the beginning of time. Move through space and that horizon moves with you. Every observer carries their own boundary of vision, always the same distance away, always unreachable. This idea can be hard to feel, because every image we've ever seen of the cosmos, every diagram, every simulation, must show an edge just to fit on a page or a screen. When we draw the universe, we draw circles, outlines, arcs. But those lines aren't real. They're symbols, not borders. If you could somehow zoom out far enough, there would be no outer shell to the universe, no black wall marking its end. You would just keep seeing more galaxies, more dark space, more light fading into faint whispers of radiation. The illusion of edges also appears in time. We imagine the Big Bang as a point in space, an explosion that burst outward into emptiness. That's the wrong picture. The Big Bang wasn't an explosion in space. It was the expansion of space itself. Every point in the universe was once closer together. The beginning happened everywhere at once. There was no centre, no outside, no before in the way we normally understand it. Time itself began with that expansion. Asking what came before the Big Bang is like asking what's north of the North Pole. The question feels sensible only because language tricks us into imagining a direction where none exists. Still, our instincts persist. We can't help but imagine boundaries, a rim to the cosmos, a frontier we could one day reach. It's a way of making the incomprehensible manageable. Even our language reveals this bias. We talk about the edge of the universe as if it were a place, something you could travel to. We speak of the beginning of time and the end of space. These phrases feel comfortable, but they're shortcuts for concepts that defy our ordinary sense of dimension. The universe doesn't have an edge any more than a circle has a corner. It's smooth, continuous, and complete in its own geometry. The strange thing is that even though the universe has no physical edges, it still produces phenomena that look like them. The event horizon around a black hole, for example, acts as an absolute boundary. Light that crosses it can never return. To an observer outside, it looks like the edge of existence, a point beyond which everything disappears. But the horizon isn't a wall. It's a region of space-time where the geometry curves so extremely that paths of light bend inward forever. It's a kind of one-way surface, defined by perception rather than material structure. The universe itself has a similar horizon, though on a cosmic scale. Beyond a certain distance, light will never reach us, no matter how long we wait. That limit isn't a border, it's a consequence of time and expansion. The same principle that gives black holes their boundaries. When you think about it that way, edges are not things in themselves but transitions, places where perception gives way to absence. The boundary of a black hole marks the transition between what can send light to us and what cannot. The cosmic horizon marks the transition between what we can observe and what lies forever beyond. Both are defined by what light can do, not by what exists physically. The universe is full of such horizons, and together they create the illusion of edges that move, shift, and disappear depending on where you stand. This interplay between perception and reality runs deep in cosmology. Even the way we measure distance depends on light's travel time. When we look at a galaxy 10 billion light years away, we're not seeing it as it is now, but as it was 10 billion years ago. Its distance isn't a single number. It changes depending on whether we mean the distance when the light was emitted, the distance the light travelled, or the distance to where the galaxy is today after billions of years of expansion. The farther we look, the less the concept of a static location makes sense. In that sense, even our idea of position is an illusion, a simplification for something far more fluid. Our need for edges shows up again in how we talk about the future. People often ask what will happen at the end of the universe. The phrase sounds natural, but it's misleading. If expansion continues as current evidence suggests, the universe will never have an end in the way a life or a story does. It will simply keep stretching, cooling, fading. Galaxies will move apart until their light no longer reaches one another. Stars will die, matter will decay, and energy will thin out until space is dark and quiet. There's no final moment, no curtain falling, just a gradual diminishing, like an echo that grows fainter but never stops entirely. The end is another illusion, born from our need for closure, and yet it's easy to understand why that illusion persists. Edges give comfort. They make things knowable. They allow us to say, here is where it stops. Infinity, on the other hand, feels heavy, too open, too vast, too impersonal. So we build edges in our minds, invisible walls that give structure to the endless. But the universe doesn't need our fences. It has its own form of order, one that exists perfectly well without boundaries. Its laws apply everywhere, from the smallest particle to the largest cluster of galaxies without exception. That continuity is its structure. There's something humbling in realizing that edges are an invention of scale. The horizon at sea feels like the end of the world, but from an airplane it becomes a circle beneath you. From orbit, even that circle disappears. Each time your perspective widens, the edge moves. What felt like a border turns out to be a curve, then a loop, then nothing at all. The universe works the same way. The more we understand it, the more we find that its edges are illusions created by limited perspective. Astronomers experience this constantly. Every time we build a more powerful telescope, we reach a new edge, the farthest light yet detected. For a while, that edge feels definitive, the limit of vision. But soon, another instrument extends it farther. The edge was never real. It was just a threshold of sensitivity. Even the word observable universe is an admission of that. It doesn't mean the universe ends there. It means our sight does. The cosmos is full of edges that aren't edges, horizons that move outward with every discovery. It's possible that this illusion is more than psychological, that it's a necessary part of being conscious within the universe. Awareness itself seems to depend on boundaries. The mind defines what it knows against what it doesn't. The self exists in contrast to the other. Our perception of edges might be an echo of that same mechanism, projected outward onto space and time. In that sense, the illusion isn't a mistake. It's the way a finite consciousness experiences an unbounded reality. And maybe that's what makes the study of the cosmos so profound. Every time we reach for the edge of understanding, we encounter a boundary that turns out not to be there. We expect walls and find windows. We expect endings and find continuations. The pattern repeats across scales, from the atom to the galaxy, from the galaxy to the universe itself. The closer we look, the more we see that reality doesn't stop. It changes, it transforms, but it doesn't end. Even our concept of outside breaks down when applied to the universe. If the universe includes everything, all space, time, matter and energy, then there can be no outside. The word loses meaning. There's no place to stand beyond it, no external perspective to view it from. The illusion of an outside is another artifact of our limited frame of reference. We think in terms of objects within containers, but the universe is not contained. It is the container, and it includes all that exists within it. What remains, then, is a kind of paradox. We live surrounded by edges that aren't real, horizons that mark not the limits of existence, but the limits of comprehension. The universe gives us borders that move, vanish, and reappear depending on how we look. Yet within those shifting limits we find meaning. The illusion of edges might be what allows us to explore at all. If the universe appeared truly infinite, with no sense of horizon, perhaps we'd never reach outward. It's the feeling of a border that draws us toward it. The illusion is both a limit and a motivation. When you look at the stars, you're seeing one of those illusions in action. The edge of the sky seems so clear, the blackness so complete, and yet, that edge is only the limit of what your eyes can register. Beyond it, light continues fainter and redder until it merges with the background radiation. Beyond that radiation, space continues to expand, filled with regions forever hidden from view. The sky you see is not the universe's outer wall. It's a layer of visibility, a thin shell of perception. And if you could somehow remove that illusion, if you could see the universe as it truly is, without the distortions of scale or time, you might find it has no edges at all, just continuity, connection, and depth. Every galaxy linked by the same fabric, every horizon a curve rather than a wall. You would see not a space surrounded by nothingness, but an unbroken structure stretching in all directions, bound only by the limits of what light can tell. That's the quiet truth hidden behind every illusion of an edge. The universe doesn't end. It changes form. The horizon isn't a line that separates existence from nothing. It's a threshold between what can be known and what waits to be discovered. The more we learn, the more those thresholds move. Every edge we find turns out to be a beginning disguised as an end. All around you, even now, there's a soft glow filling the universe. You can't see it with your eyes, and you can't feel it on your skin, but it's there. A faint warmth that comes from every direction. If you could tune your senses to microwave frequencies, you would find that space itself hums with it, a gentle background that never fades. It isn't the light of stars or galaxies, or any single object. It's older than all of them. It's the remnant of the moment the universe became transparent, the first light ever to travel freely. It is quite literally the afterglow of creation. Scientists call it the cosmic microwave background, but to think of it more simply, it's the universe's whisper, a quiet memory from a time when everything began. That whisper has been travelling for almost 14 billion years. It began when the universe was just 380,000 years old, a time when it was still glowing, hot and dense, filled with a fog of particles and radiation. Before that moment, light couldn't move freely. The cosmos was opaque, a blinding plasma where photons scattered constantly off electrons and protons. But as the universe expanded, it cooled, and at a certain temperature, around 3000 degrees Kelvin, the fog cleared. Electrons combined with protons to form neutral hydrogen atoms, and suddenly, light was free to travel. Those first photons have been on the move ever since, stretching with the expansion of space, cooling from visible light to microwaves, until they became what we detect today, a faint background radiation, just a few degrees above absolute zero. To detect that light, is to touch the earliest visible surface of the universe. Not in space, but in time. Every direction you look, the microwave background glows with almost perfect uniformity. It's the same wherever you point an antenna, the same in every galaxy, the same for every observer no matter where they are. It's not the echo of a single explosion, but the collective radiation of the entire cosmos at once. That's why it's so special. It's the oldest light we can see, the cosmic horizon of visibility, a photograph of the universe as a baby. The discovery of that background was almost an accident. In 1965, two radio engineers, Arno Penzias and Robert Wilson, were testing a large horn-shaped antenna in New Jersey, built for satellite communications. They kept detecting a faint noise that wouldn't go away, a persistent hiss coming from all directions, day and night, regardless of where they pointed. They checked everything. They cleaned the equipment, removed what they thought were nests from pigeons inside the antenna, recalibrated their instruments. Still, the noise remained. Around the same time, a group of physicists just 30 miles away at Princeton University, led by Robert Dicke, had been working on a theory predicting exactly such a signal, the residual radiation from the Big Bang. When they learned about Penzias and Wilson's noise, the pieces fit perfectly. What they had discovered was the glow of the early universe. That discovery changed cosmology forever. Before it, the Big Bang was one of several competing theories about the universe's origin. Some scientists favoured a steady-state model, a cosmos with no beginning, where new matter continually appeared to keep the density constant as space expanded. The detection of the cosmic microwave background ended that debate. A steady-state universe would have no reason to emit a faint uniform glow. But a universe that began hot and dense, then cooled over time, would naturally leave behind just such a relic. The hiss that Penzias and Wilson couldn't eliminate was, in fact, the sound of confirmation, the first direct evidence that the universe had a beginning. Since then, the study of that faint radiation has become one of the most important tools in cosmology. The uniformity of the background tells us that the early universe was remarkably smooth, the same density and temperature everywhere, to within 1 part in 100,000. But those tiny imperfections, the minuscule ripples in that smoothness, are what made everything we see today. Regions that were slightly denser drew in more matter over time, eventually forming galaxies, stars and planets. In that way, the background isn't just an echo of the past, it's the blueprint of the present. Every structure in the universe traces its origin back to those faint fluctuations imprinted on that early light. When we look at maps of the cosmic microwave background, we're seeing those ripples frozen in time. Satellites like COBE, DeepMap and Planck have measured them in exquisite detail, mapping the entire sky at microwave wavelengths. The images they've produced are astonishing, a mottled pattern of tiny temperature variations, just millionths of a degree apart, stretched across the heavens. Each blotch corresponds to a region in the early universe that was slightly warmer or cooler than average. Together they form a cosmic fingerprint, unique and complete, encoding the information about the universe's age, composition, and geometry. From those patterns, scientists have extracted astonishing knowledge. The data tells us that the universe is about 13.8 billion years old. It tells us that about 5% of its content is ordinary matter, the stuff that makes up stars, planets, and people. Around 27% is dark matter, invisible but gravitationally real, and the rest, about 68%, is dark energy, the mysterious force driving the accelerated expansion of space. All of that information is contained in the slight irregularities of a signal that began before the first galaxies existed. The uniformity of the background also supports one of the strangest but most important ideas in cosmology: inflation. The fact that the background looks the same in every direction means that distant regions of the universe, now separated by tens of billions of light years, must once have been in contact, close enough to share heat and come into equilibrium. That's only possible if the universe expanded extremely fast in its earliest moments, faster than light could travel, stretching a tiny uniform patch into the vast cosmos we see today. Inflation explains the smoothness of the background, the flatness of space, and the absence of magnetic monopoles, all puzzles that otherwise make little sense. To see that logic written in faint microwaves is a reminder of how subtle the universe's memory is. The background radiation isn't bright. Its temperature is just 2.725 Kelvin, barely above absolute zero. Its photons are so spread out that each cubic centimetre of space contains only a few hundred of them, and yet they fill all of space evenly, unbroken, unending. They pass through you every moment, through the walls, through the air, through the earth. The entire universe is bathed in them, a quiet sea of ancient light. In a way, that glow connects everything. The light that left those early atoms has travelled unimpeded through every region of space, threading through the formation of galaxies, through clusters, through voids. It's a universal background, the same for all observers. Whether on Earth, in a distant galaxy, or in another corner of the cosmos entirely, any civilization with a sensitive enough detector would see the same pattern, the same whisper. It's the one message that unites the entire universe, a shared origin written in radiation. The cosmic microwave background is also, in a sense, the farthest we can ever see. It's the surface of last scattering, the moment when light and matter decoupled. Before that, the universe was too dense for light to travel freely, so no telescope, no matter how powerful, can see beyond it using electromagnetic waves. To look earlier, we'd have to find other messengers, neutrinos, gravitational waves, perhaps something even more fundamental. But for now, the microwave background remains the edge of light's reach, the outer boundary of vision. Beyond it lies only theory. And yet, what we can see is more than enough to fill a lifetime of wonder. When the Planck satellite released its map of the cosmic background in 2013, scientists noticed tiny asymmetries, minute differences in temperature from one hemisphere of the sky to the other. Some of those variations might be statistical, others might hint at new physics. Perhaps the universe isn't perfectly uniform after all. Maybe inflation had ripples of its own, or maybe there's structure beyond our horizon, faintly influencing what we can observe. The whisper still carries mysteries. It's remarkable that such a faint signal can tell us so much. The data from the microwave background doesn't come from bright spots or sharp features. It comes from small differences in temperature, a few microkelvin here, a few there. Extracting meaning from it requires extraordinary precision. Scientists build detectors cooled to fractions of a degree above absolute zero, placed on satellites far from Earth's interference, measuring photons that have travelled for nearly the entire age of the universe. The instruments must distinguish between signals 1,000,000 times fainter than the microwave radiation of our own atmosphere. The fact that we can do that we can hear the universe's whisper through the noise of our own planet, is one of the quiet triumphs of human ingenuity. When you step back and think about it, that whisper is everywhere. The static you see on an old television screen, the random snow that flickers between channels, is partly made of those ancient photons. About 1% of that static is the afterglow of the Big Bang. Every time you've ever looked at that noise, you've been seeing the oldest light in the universe, unknowingly catching a glimpse of creation itself. It's a hum that never stops, a reminder that even in the silence of space, something is always speaking. The cosmic microwave background isn't loud, but it's persistent. It fills every frequency, every point, every moment. It's the baseline of the universe's soundscape, the foundation upon which all later structures were built. Without it, we wouldn't know the universe's age, composition, or geometry. Without it, we wouldn't even be sure that there was a beginning. That faint uniform glow is the universe's autobiography, written in temperature and wavelength. It's strange to think that such an old signal still exists, untouched, unchanged except by the expansion of space. Most things decay, fade, or evolve, but the microwave background endures. It's not an echo that weakens. It's a constant presence stretched thinner as the universe grows. It carries the same energy, spread across a larger and larger volume. The older the universe becomes, the cooler and dimmer that light will be, until eventually it's undetectable. Trillions of years from now, future observers, if there are any, will no longer see it. The cosmic whisper will fade into absolute quiet. But for now, in this moment of cosmic history, we can still hear it. We live in a rare era, late enough for the universe to have grown complex, early enough that its first light still reaches us. The microwave background connects us directly to the beginning, a bridge across nearly 14 billion years. It's as if the universe is still mid-sentence, still speaking from its own origin, and we've arrived at the precise moment when the words are just audible. Every act of listening, every detection, brings us closer to understanding how the universe grew from that glowing plasma into the vastness we see today. The tiny ripples in the background are not random. They follow a statistical pattern predicted by quantum fluctuations, minute variations in density that inflation magnified to cosmic scale. The structure of the entire universe began as microscopic differences in energy. From those small irregularities came everything: galaxies, stars, planets, life. The whisper of the early universe contains the blueprint for all of it, and perhaps that's the most humbling thought of all, that the faint noise filling space is not just a remnant of something long gone, it's a reminder of continuity. The same light that left when the first atoms formed is still here, touching everything. The photons that drift through your body right now began their journey before the Milky Way existed. The universe, in its quietest form, has been travelling through us all along. The cosmic microwave background is not just evidence of what happened. It's a symbol of what remains, the persistence of information, the endurance of light. It's the closest thing the universe has to a memory, and through it, we remember too. When we measure it, we are listening to time itself breathing softly through the dark. The more we learn about the universe, the more we realize how much of it remains unknown. The stars and galaxies we see, the planets we can map, the light we can trace, all of that, everything visible, makes up only a small fraction of what's really there. The rest is hidden, silent, unseeable, yet overwhelmingly real. The universe, as far as we can tell, is built mostly from things we cannot detect directly. The further we look, the deeper that mystery grows. It's as though every discovery only widens the shadow it was meant to illuminate. The expanding unknown isn't a metaphor, it's a literal description of what's happening as we explore the cosmos. When astronomers map the sky, they're not just measuring light, they're measuring gravity, the way galaxies pull on one another, the way clusters bend space, the way motion reveals mass. Those measurements show something remarkable. There's far more mass in the universe than the light suggests. Galaxies spin too fast for their visible stars and gas to account for their gravity. Clusters of galaxies hold together more tightly than their luminous matter can explain. Light from distant sources bends more strongly than it should as it passes through space. Something unseen is shaping those effects, something that doesn't emit, absorb, or reflect light, but interacts through gravity. That unseen presence is what we call dark matter. Dark matter makes up about 27% of the universe's total energy content. It outweighs ordinary matter by more than 5 to 1. Yet we've never detected a single particle of it directly. It doesn't collide with atoms, it doesn't glow, it doesn't leave trails in our detectors. Its existence is known entirely through its influence, through the way it holds galaxies together, through the way it sculpts the cosmic web, through the way it bends light from distant objects. It's the invisible scaffolding of the universe, the the skeleton upon which all visible matter hangs. Without it, galaxies like the Milky Way wouldn't exist, stars would never have formed, planets and everything on them would never have come to be. Scientists have spent decades trying to identify what dark matter actually is. There are many possibilities. Theoretical particles with names that sound almost poetic, WIMPs for weakly interacting massive particles, axions, tiny hypothetical particles that might fill space like a faint mist, sterile neutrinos, elusive cousins of the ordinary neutrinos that pass through everything unnoticed. Despite countless experiments, none have been found. Detectors buried deep underground, designed to catch even the faintest collision between dark matter and ordinary matter, have remained silent. Particle accelerators like the Large Hadron Collider have yet to reveal any new candidates. For now, dark matter remains a name for something we don't understand, a placeholder for the invisible mass that keeps the universe coherent. Its effects, though, are undeniable. If you could see gravity instead of light, the universe would look completely different. You would see vast filaments stretching across cosmic space, connecting clusters of galaxies like strands in an enormous web. Those filaments are made mostly of dark matter, with luminous galaxies forming along their densest threads. Between them lie enormous voids, regions of near emptiness where even dark matter thins. The pattern is astonishingly consistent across scales, a fractal structure built by gravity and time. The galaxies we see are like frost forming on the outlines of an invisible structure. And beyond dark matter lies something even stranger. Something that doesn't just hold the universe together but pushes it apart. That force is called dark energy. It makes up nearly 70% of everything that exists. It's the energy of empty space itself, a kind of cosmic pressure that drives the accelerated expansion of the universe. When astronomers first discovered that expansion was speeding up, they were stunned. They had expected gravity to slow it down over time, perhaps even to halt it someday. Instead, the opposite was true. The galaxies were not only moving apart, they were doing so faster and faster. Something was overpowering gravity on the larger scales, and that something was everywhere. Dark energy is one of the most profound mysteries in all of physics. It doesn't behave like matter or radiation or any known field. It doesn't clump or collapse. It simply exists. A smooth, uniform energy that fills all of space. Its density remains constant as the universe expands, which means that as space grows, the total amount of dark energy increases. The more space there is, the more dark energy there is to drive expansion. It's a self-reinforcing process, one that leads to an outcome both fascinating and unsettling. The acceleration will continue indefinitely. Galaxies will move farther and farther apart, until eventually the only ones left visible will be those gravitationally bound to us. The small cluster containing the Milky Way, Andromeda, and a few others. Everything else will fade beyond the horizon, their light stretched beyond detectability. The universe's expansion will continue quietly, endlessly, until it becomes cold and still. The nature of dark energy remains unknown. It could be a cosmological constant, a fixed property of space, as Einstein once proposed and later discarded, only for it to return triumphantly decades after his death. Or it could be something dynamic, a field that changes over time, slowly altering the fate of the universe. It might even be a sign that our understanding of gravity itself is incomplete, that the equations we use to describe space-time need to be modified on the larger scales. Whatever it is, it dominates everything, shaping the evolution of the cosmos more than any star or galaxy ever could. It's strange to realize that the universe we can see, the part filled with light and life, is only a small minority of what exists. Ordinary matter, atoms, elements, dust and gas, accounts for less than 5% of the total. Everything else is dark, invisible, and largely unknown. The universe, in essence, is a shadow play. The bright points we observe are only the visible edges of a deeper structure, one that hides more than it reveals. The more we understand, the more that unseen reality expands. Even the space between galaxies, the regions we call empty, isn't truly empty. It's filled with quantum fields, fluctuating, restless, alive with potential. The vacuum itself has energy, though its exact amount is a mystery. Theoretical calculations of the vacuum's energy predict a value so enormous that, if correct, the universe would have torn itself apart instantly after the Big Bang. The fact that it didn't means we're missing something fundamental. Perhaps there's a cancellation we don't yet understand, or perhaps the vacuum energy we measure as dark energy is only a small remnant of a much larger balanced field. Quantum mechanics tells us that even in perfect vacuum, particles flicker in and out of existence, virtual pairs that appear, interact, and vanish almost instantly. On tiny scales, space is not smooth but seething, a restless foam of probabilities. On cosmic scales, that same restless foundation may be what gives rise to dark energy. The expanding unknown isn't just out there, in the distant reaches of space. It's also right here, woven into the emptiness around us. The universe hides its strangeness not behind distance, but behind familiarity. There's another layer to the unknown, one that doesn't just expand with the universe, but defines its beginning. The laws of physics as we know them work beautifully for almost everything, but they break down at the very start, at the singularity of the Big Bang, where density and temperature become infinite. At that point, gravity and quantum mechanics collide, and our equations fail. We don't yet have a theory that unites them. Somewhere between Einstein's geometry of space-time and the probabilistic world of quantum fields lies a deeper framework that could explain the origin of both matter and energy. We call it quantum gravity, but we don't yet know what it looks like. The search for that theory, through ideas like string theory, loop quantum gravity, and holographic principles, is the next frontier of understanding. But for now, the beginning remains hidden behind a veil of mathematics we have not yet learned to read. As vast as the unknown is, it's not empty of meaning. It's a reminder that knowledge itself has edges, just as the observable universe does. Those edges move as we learn more, but they never disappear. The expanding universe is matched by an expanding frontier of ignorance. Every discovery pushes the horizon outward, revealing new mysteries beyond. When we found dark matter, we thought we were nearing a complete picture. Instead, we discovered that most of the cosmos was invisible. When we found dark energy, we thought we were filling in a missing piece. Instead, we learned that the largest influence on the universe is something we can't describe. Each answer brings more questions, not fewer. And yet, this isn't discouraging. It's what makes science feel alive. The unknown isn't a void waiting to be filled. It's the environment that makes discovery possible. The universe's greatest mysteries, dark matter, dark energy, the nature of time, the origin of the laws themselves, aren't obstacles. They're invitations. They're signs that reality is deeper than we thought, that our understanding is still unfolding. The expanding unknown isn't a failure of comprehension. It's the very essence of curiosity. There's also a kind of symmetry in it. Just as the universe expands physically, stretching space itself, our awareness expands mentally, stretching the boundaries of what can be known. Both processes are open-ended. Neither has a final destination. The more we measure, the more the unknown grows, not because it resists us, but because each answer reveals new depths. It's an expansion not of defeat, but of perspective. If you think of the universe as a vast ocean, then what we know is like a thin layer of sunlight near the surface. Bright, detailed, and beautiful, but shallow compared to the dark depths below. The light of understanding doesn't end where the darkness begins. It simply grows dimmer, blending into mystery. That boundary isn't a wall, it's a gradient, and we live right on it, suspended between knowledge and wonder. Even our place within this unknown is uncertain. We know our galaxy is one among billions, but we don't know whether our universe is one among countless others. Some theories suggest that cosmic inflation might have created multiple universes, each with its own laws of physics, a multiverse where every possible configuration of reality exists somewhere. It's an idea we can't test, perhaps one we never will, yet it may be the most natural outcome of the same physics that shaped our own cosmos. If that's true, then even the universe we see, immense as it is, might be just one bubble in an endless sea. That possibility changes how we think about the word everything. If there are other universes, then everything is no longer the whole. It's just one instance among many, one variation in an infinite pattern. But even that doesn't lessen the wonder. It deepens it. The unknown doesn't shrink meaning, it expands it. It reminds us that the story we're part of is not small, not confined to what we can see or measure, but part of something much vaster. It's easy to imagine that someday humanity might solve these mysteries, that we'll identify dark matter, understand dark energy, unify physics, and see the beginning clearly. But even if that happens, new mysteries will appear. The universe will not run out of questions. It's not a puzzle to be completed, it's a process without end. Each solution refines the unknown rather than erasing it. The expansion of ignorance is the shadow of progress. So as the physical universe continues to stretch, carrying galaxies farther apart and dimming the light between them, the unknown expands too. Not as darkness, but as space for imagination, curiosity, and wonder. The more we know, the more we realize how much remains unseen. And in that realization, there's a strange kind of peace. Because maybe the purpose of knowing isn't to eliminate the unknown, but to learn how to live within it, to let it remind us of scale, of perspective, of humility. The expanding unknown isn't something to fear, it's the place where understanding grows. The horizon of mystery is not a wall, it's a mirror reflecting back the limits of our own perception, inviting us to look closer. There's a quiet moment when you've thought about the universe long enough, when a strange idea begins to form. If space stretches forever, if the laws of physics are the same everywhere, if the cosmos keeps expanding beyond the horizon of what we can ever see, then maybe our universe isn't the only one. Maybe what we call the universe is just one bubble in a vast and unseen sea. The thought arrives gently, almost as a whisper, yet it changes everything. Because if it's true, then the story of existence is much larger than the space we inhabit. It becomes not a single universe, but a multiverse, a landscape of countless realities, each governed by the same or slightly different rules, each expanding, evolving, and drifting like foam on an endless ocean. The notion of multiple universes isn't new. Philosophers have imagined it for centuries, long before physics had the tools to explore such an idea. But in the past few decades it has emerged not just as speculation, but as a possible consequence of real theories, the natural outcome of the same physics that describes the beginning of our universe. In trying to understand how space and time began, scientists have stumbled upon scenarios that make multiple universes not only plausible, but almost unavoidable. The more we learn about cosmic inflation, quantum mechanics, and the structure of reality, the more this idea seems to follow us, quietly but persistently, like a reflection we can't quite ignore. To see how it arises, we need to return to the earliest moments after the Big Bang, or rather before the universe became what we recognize as the Big Bang at all. According to inflation theory, the universe began as a tiny region of space filled with a peculiar kind of energy, one that caused it to expand exponentially, doubling in size again and again in less than a fraction of a second. That inflation didn't just make the universe large, it made it smooth, flat and uniform, explaining why the cosmic microwave background looks so even in every direction. When inflation ended, the energy driving it transformed into the matter and radiation that would become stars, galaxies, and everything else. But the equations that describe inflation suggest it might not have ended everywhere at once. In some regions, the process could have stopped, giving rise to universes like ours. In others, it could have continued, producing new bubbles of space, each expanding, each potentially developing into its own universe, each separated by vast, impassable voids of inflating space. This idea is called eternal inflation. It means that while our observable universe may have stopped inflating billions of years ago, inflation as a whole never truly ended. Somewhere, far beyond what we can see, new universes may still be forming, endlessly budding off from an infinite cosmic field. Each of those universes would be isolated from the others, expanding too fast for any communication between them. They could have different properties, different laws of physics, different numbers of dimensions, even different constants of nature. In one, gravity might be stronger. In another, atoms might not form at all. Some would collapse instantly, others would expand forever. Most might be lifeless, but few could resemble ours closely enough to allow stars, planets, and consciousness to arise. If this picture is correct, then our universe is just one of countless possibilities. One region where conditions happen to align in a way that allowed us to exist. It's an unsettling idea at first. It removes the comforting sense that the universe we see is all there is, that our physical laws are universal and complete. But it also resolves one of science's deepest puzzles: why the constants of nature seem so precisely tuned for life. The strength of gravity, the charge of the electron, the mass of the proton, the cosmological constant. Each of these values lies in a narrow range that allows matter to form, stars to burn, and chemistry to exist. Change any of them slightly, and the universe would be sterile. In a single universe picture, that fine-tuning is a mystery. But in a multiverse, it becomes inevitable. If there are countless universes, each with different physical parameters, then some of them will naturally have the right conditions for life, just by chance. We find ourselves in one of those not because it's special, but because we couldn't exist in any other. Still, there's something deeply human about wanting to know what lies beyond even that. If there are other universes, could they ever interact? Could one leave an imprint on another, some faint signature in the cosmic microwave background, or the distribution of galaxies? Theoretically, if two universes ever collided during inflation, they might leave behind a circular mark, a pattern of temperature variations imprinted on the cosmic background radiation. Some scientists have searched for such signs, scanning maps of the sky for evidence of these cosmic bruises. So far, no clear evidence has been found. But the possibility lingers. The sky we see could, in principle, contain the faint memory of another universe brushing against ours in the distant past. The idea of multiple universes also finds echoes in the quantum world, where the behavior of particles defies our usual sense of logic. In quantum mechanics, every event has a range of possible outcomes, each with a certain probability. When we make a measurement, we see one outcome, but what happens to the others? One interpretation, known as the many worlds interpretation, suggests that all possible outcomes occur, each in its own branch of reality. When a particle's wave function collapses here, it expands elsewhere, splitting the universe into countless versions, each as real as the next. In that view, the multiverse isn't something far away. It's happening all the time, everywhere, at every moment, branching endlessly as quantum possibilities unfold. It's hard to imagine such a reality, not because it's complex, but because it's too large for the human mind to hold. Every decision, every random quantum event would produce new versions of the universe. Somewhere, there's a version of you who turned left instead of right, who spoke instead of staying silent, who lived a slightly different life. The differences might be small or vast. In one, you might not exist at all. The multiverse, in that sense, isn't just a feature of physics. It's a reflection of how reality could contain every possibility at once. Whether the multiverse arises from cosmic inflation or quantum mechanics, the pattern is the same: repetition and variation across scales. The universe we inhabit is one expression among many. Each follows its own path, governed by its own version of the same underlying laws. The term multiverse might sound extravagant, but it's really just the logical extension of what we already know, that nature doesn't waste possibilities. Wherever a process can occur, it does, somewhere, sometime. The multiverse could be the grandest expression of that principle, the ultimate realization of the idea that existence explores every option. Of course, none of this is proven. The multiverse remains a hypothesis, supported by theory but not by direct evidence. Some physicists see it as an unavoidable consequence of inflation and quantum mechanics. Others see it as a philosophical distraction, an idea that can't be tested and therefore lies outside the realm of science. It may never be resolved because the other universes, if they exist, are forever beyond our cosmic horizon. We could live in an infinite sea of universes and never know it, because light from those regions could never reach us. The multiverse may be real, but it may also be unprovable, a truth that can only be inferred, never observed. And yet, even if it's beyond proof, the idea carries meaning. It expands what we mean by reality. It reminds us that the limits of observation are not the limits of existence. Just as we once believed the Earth was the centre of everything, only to discover it was one planet among many, then one star system among billions, we may one day accept that our entire universe is just one region among countless others. The scale keeps expanding, and with it, our sense of what's possible. Sometimes people ask whether the existence of other universes would make ours less special. It might seem that way at first, that if there are infinite versions of reality, then any one of them, including ours, loses significance. But the opposite is true. Each universe, each possible configuration of matter and energy is unique. Our universe is special precisely because it exists. Because within this one, these exact laws of physics gave rise to galaxies, to life, to consciousness capable of asking the question. The existence of others doesn't diminish that. It enriches it. It makes reality larger, more intricate, more profound. It's also possible that we're already part of something like a multiverse without realizing it. Within our own universe, there are regions of space so distant that light from them will never reach us, separated forever by the acceleration of expansion. To us, they're effectively separate universes, unreachable, unknowable, but governed by the same physics. The boundaries of communication become the boundaries of reality. The universe, in that sense, is already fractured into billions of isolated domains, each with its own future, its own horizon. The multiverse might not be a separate concept at all. It might be simply what happens when infinity evolves. There's another way to think of it, one that blends the scientific with the reflective. Perhaps the multiverse isn't just a physical reality, but a metaphor for perception. Each consciousness experiences its own version of the universe, shaped by perspective, memory, and understanding. No two observers see the same sky in exactly the same way. Each of us carries a universe of perception, bound by the limits of our awareness. The physical multiverse might be beyond reach, but the mental one, the one made of experiences and possibilities, is something we live inside every day. When you consider that idea long enough, it begins to sound less like speculation and more like a continuation of everything we've already learned. The universe has always surprised us by being larger, stranger, and more interconnected than we expected. Every time we thought we'd found its edge, we discovered another layer beyond. The multiverse is simply the next step in that pattern, the next horizon of imagination. It's what happens when the expanding unknown grows beyond even our definition of universe. And yet, even as we entertain these vast possibilities, there's comfort in knowing that our small corner of reality, this galaxy, this solar system, this moment in time, is enough. Whether or not there are infinite other universes, this one is complete in itself. The light from the stars still crosses the void. The laws of physics still hold. The same constants that shaped galaxies shaped us. We're part of whatever larger structure exists, connected by the same fabric of existence, whether or not we ever see its full extent. The idea of mirrors, reflections across realities, comes naturally when thinking about this. The multiverse is, in a way, a hall of mirrors. Each universe reflects a different version of the same fundamental principles, the same quantum possibilities, the same cosmic seeds. Some reflections might be similar, others distorted, others unrecognizably different. But they all share one source, the same underlying reality, refracted through variation. The mirrors might stretch forever, but they all reflect light from the same origin. It's possible that someday, if our understanding deepens enough, we'll find indirect signs of those reflections. Maybe subtle correlations in the cosmic microwave background. Maybe gravitational echoes of other bubble collisions. Maybe a pattern in quantum fluctuations that hints at interaction across unseen boundaries. If that ever happens, it would be the greatest discovery imaginable. Evidence that our universe is not alone. But even if that day never comes, the idea itself serves a purpose. It reminds us that we are not limited by what we can see. The mirrors of possibility stretch beyond sight, and the light that fills them is the same light that fills us. And perhaps that's the quiet truth behind the concept of the multiverse. Not that there are infinite copies of everything, but that existence itself is infinite in expression. Every configuration of energy, every pattern of space and time is a variation of the same fundamental essence. Whether we call that essence the laws of physics, or the fabric of reality, or simply the universe itself, it's all one thing seen from different angles. The mirrors don't separate us from the whole, they reveal its depth. Somewhere beyond our cosmic horizon, other universes may still be forming, expanding and evolving, each with its own sky, its own story. We'll never see them, but the thought of their existence changes how we see our own. It adds dimension to our understanding, not in space, but in meaning. It shows that reality is larger than any single description, and in that vastness there's a quiet, enduring beauty, the sense that no matter how far we go, there will always be another reflection waiting, another light glimmering just beyond the reach of vision. And from those reflections, we return again to the one that looks inward, the reflection of ourselves, the observers within the story. Because the more we learn about the universe, the more we realize that we are part of the same mystery we're trying to solve. The edge between the observer and the observed fades, like a mirror slowly merging with its image. The multiverse, in that way, isn't just out there. It's here, in the act of wondering itself. For as long as people have been looking up, we've wondered what lies beyond what we can see. The night sky has always been a mirror for that question. Its distances invite imagination. Its silences demand interpretation. Yet the more we learn about the universe, the more it seems to turn the question back toward us. The cosmos stretches beyond measure, but so does the mind that contemplates it. Somewhere between the vastness outside and the awareness within lies a horizon. Not made of light or distance, but of understanding. The human horizon. We spend a great deal of time measuring things, the distances between galaxies, the lifetimes of stars, the rate at which the universe expands. But what we're really doing is measuring our relationship to mystery. Every new telescope, every discovery, every equation expands that relationship outward. We learn to see farther, to describe more precisely, to know in greater detail what surrounds us. But knowledge is never just about accumulation. It's about perspective, the widening of context, the recognition that every new insight places us in a larger frame. When you think about the universe as a whole, it's easy to feel small. The scales are beyond comprehension. Even the nearest star is so far that light takes years to cross the gap, and the galaxies beyond are millions or billions of light-years away. On those scales, human life seems almost too brief to matter. But scale alone doesn't measure significance. The atoms that make up your body were forged in stars that lived and died billions of years ago. You're literally built from the remnants of ancient light. The carbon in your cells, the iron in your blood, the calcium in your bones, all of it was born in stellar furnaces. You're not separate from the cosmos. You're a continuation of it, a recent expression of matter's long and intricate journey. When we study the universe, we're studying our own origin story. The hydrogen that fills the galaxies, the dark matter that shapes them, the cosmic background radiation that hums through all of space. All of it connects directly to us. The same laws that govern the movement of galaxies also govern the neurons in your brain. The same constants that determine the orbits of planets determine the bonds between atoms in your body. There is no break between the human and the cosmic. The difference is one of scale, not substance. The horizon that seems to separate us from the stars is in truth a boundary of perception. This understanding changes what we mean by exploration. The search for knowledge about the universe is not a conquest of the unknown, it's a dialogue with it. Every discovery is a new sentence in a conversation that's been unfolding for billions of years. The universe produces consciousness, and consciousness reflects on the universe. That loop, that quiet, recursive awareness, might be the most extraordinary structure in existence. Through us, the cosmos becomes self-aware. Through our questions, it begins to know itself. It's worth pausing to consider what that means in practical terms. The light from distant galaxies we capture in telescopes is ancient. It began its journey long before Earth existed. When it finally reaches our instruments, it completes a process that began before our species appeared. Every observation is a reunion across time. Every photon that enters our eyes or our detectors carries the story of a universe that has been expanding, cooling, and changing since the beginning. When we study that light, we're not just learning about distant objects. We're participating in a cycle of cosmic awareness. Energy from the early universe meeting the minds it eventually gave rise to. That realization has a kind of quiet symmetry. We look outward to understand the universe, but in doing so, we also look inward. The more we learn about how the cosmos works, the more we see that consciousness itself follows similar patterns: expansion, complexity, self-organization, evolution. The human mind mirrors the structure of the universe in miniature. Networks of neurons form connections that resemble the clustering of galaxies. Thoughts move through pathways like matter flowing along cosmic filaments. Awareness expands not by erasing mystery, but by integrating it, by seeing patterns where there were once walls. Our horizon as a species has changed many times. For most of history, humanity's known universe was the sky above and the land below. The stars were lights fixed in a dome, their purpose mysterious, their distance unimaginable. Then we learned that Earth orbits the Sun, that the Sun is one of many stars, that our galaxy is one of countless others. Each step expanded the horizon and diminished our sense of centrality. But with every loss of imagined importance came a gain in understanding. The more we've realized that we're not at the center, the more meaningful our existence becomes. We're not privileged observers, we are participants in a vast and ongoing process. The human horizon isn't defined only by what we can see. It's also shaped by what we can imagine. Every scientific theory begins as a question that reaches beyond current evidence. Imagination pushes the horizon outward before data catches up. The concept of atoms, the structure of DNA, the curvature of space, all began as ideas before they became measurable. The human ability to think beyond what's immediately observable is one of the universe's most extraordinary phenomena. It's as though reality built into itself a way to exceed its own boundaries, using us as its mechanism. And yet, for all that expansion, there are limits we can't cross. The speed of light sets an ultimate barrier for information. The cosmic horizon defines how far we can see. The laws of thermodynamics constrain what we can do. These limits are not arbitrary, they're structural. They're what make reality coherent. Without them, there would be no causality, no time, no stable existence. The boundaries of physics are what allow the universe to persist long enough for life to emerge. The horizon is not an obstacle to meaning. It's the frame that gives meaning shape. Sometimes it feels like those limits should frustrate us. We can't travel to the stars, can't see the universe's beginning directly, can't know everything. But maybe that's the wrong way to see it. Perhaps the horizon exists not to restrict, but to guide curiosity. If there were no edges to perception, there would be no direction for exploration. The unknown defines the path of learning. Each horizon we reach reveals another beyond it, and the journey continues not despite that, but because of it. It's the same on smaller scales. In every field of study, physics, biology, philosophy, there's a boundary where certainty ends. Those edges are where discovery happens. The human horizon is not fixed. It expands through effort, through thought, through the quiet persistence of wonder. The more we look, the more we understand that knowledge is an ongoing act, not a final state. The horizon is always moving, always receding, inviting us to follow. There's also a personal version of this horizon, the one that defines each life. Everyone carries their own limit of understanding, their own edge of perception. Some find it in science, others in art, others in silence or reflection. Each of us explores the universe from a slightly different angle, adding one more perspective to the total picture. The collective horizon of humanity grows as individuals push theirs outward. Every act of curiosity, every question asked in earnest, widens that shared boundary. When you think of it that way, even small moments, a child looking at the moon, a student discovering a new equation, an artist painting a star field, become part of the same grand expansion. The human horizon grows not only through technology or data, but through attention. To notice the world carefully is to extend understanding. Every observation, however ordinary, participates in the same process as the great discoveries of science. It's easy to forget that we are living through one of the most extraordinary times in human history. We've mapped the cosmic background radiation, traced the evolution of galaxies, detected gravitational waves, and seen images of black holes. We've built machines that can look billions of years into the past, reading light that has travelled across most of cosmic history. And yet, the core of what drives all this remains the same as it was thousands of years ago. A question spoken into the dark. What is this? Where are we? How far does it go? The instruments have changed. The wonder has not. If you could step back far enough, if you could see humanity from a cosmic distance, you might see it as a flicker of light on the surface of a small planet. But that flicker is significant. It's the universe waking up to its own existence. It's the first faint glow of awareness in an otherwise silent expanse. The galaxies might not know they exist, but we do. That knowledge, fragile and temporary though it may be, is one of the universe's rarest phenomena. It's a kind of light that doesn't fade with distance, because it exists in understanding, not in space. As we continue to explore, both outward and inward, that light grows. Our technology extends our senses. Our thinking refines what we can imagine. We send probes to other planets, telescopes into deep space, detectors beneath the Earth, algorithms into data, and each one extends the reach of perception. But even as the tools evolve, the essential act remains the same. Looking into the unknown and listening for a response. The human horizon is defined not by what we've reached, but by what we're still reaching for. It's possible that, in the far future, humanity will fade. Civilizations rise and fall, planets change, stars die. The horizon will continue to move whether or not we're here to see it. But the fact that we've existed at all, that we've thought about the universe, measured it, loved it, feared it, is enough. For a brief moment, the cosmos became aware of itself through us. The light of that awareness, once sparked, doesn't need to last forever to have meaning. It's enough that it happened. And even if the universe continues without observers, the laws that made awareness possible will remain. The same physics that created galaxies also created minds. The same processes that shaped stars shaped thought. To contemplate that is to see that consciousness is not an accident, but a natural expression of the universe's complexity. Wherever matter becomes organized enough, awareness may arise again, perhaps differently, perhaps more fully. The horizon of understanding is not just ours, it's the universe's own capacity to know itself, unfolding in countless forms. That realization turns the vastness of the universe from something intimidating into something intimate. The distances don't diminish us, they connect us. Every atom in your body participates in the same cosmic evolution as the atoms in the stars. Every breath carries traces of hydrogen from the first moments of creation. When you look up, you're not looking away from home, you're looking into it. The horizon isn't out there, it's everywhere, including within. And maybe that's what it means to be human in a universe like this, to live at the intersection of knowledge and mystery, to keep expanding the horizon without ever reaching its end. The unknown doesn't close in on us, it invites us forward. The sky is not a boundary, it's a beginning. The universe does not end where our understanding stops. It continues quietly waiting for the next question. And beyond that thought, another horizon begins to form, one that isn't cosmic or human, but something deeper, something shared between both. It's the horizon of wonder itself, the place where knowledge fades into awe, where we stop asking and start listening again. Because at the edge of everything we know, there's always that quiet sense of reverence, the awareness that the universe, for all its vastness, still holds mysteries too beautiful to ever be solved. There comes a moment in every long exploration, whether of the world or the mind, when you realize you've stopped moving outward and started simply looking around. The search for understanding brings you so far until what remains is not distance, but depth. You begin to notice not how far the universe extends, but how complete it already is. You see that the mystery you've been chasing isn't hiding at the edge of the cosmos. It's present in every part of it, in every atom, every pulse of light, every breath. That's what it feels like to arrive here, at the edge of wonder. Not the end of a journey, but the place where exploration turns into quiet awareness. The universe has a way of humbling even the most persistent curiosity. We've spent centuries mapping the heavens, building instruments that can reach billions of light years into the past. We've described the birth of stars, the collapse of black holes, the shape of spacetime itself. We've followed light to its limit, traced it back to its first moments, and still there's no sense of completion. Every discovery opens more questions than it answers. The closer we look, the more we find. The horizon keeps moving. The wonder remains intact. That constancy, the fact that wonder never runs out, might be the universe's most beautiful feature. It means that the story never ends. Even as galaxies drift apart and the stars slowly die, the act of perceiving, of asking, of imagining continues. The universe, in its own quiet way, has built into itself the capacity for awe. You can see it in the simplicity of physics, in the elegance of equations that describe everything from light to gravity, in the symmetry that underlies every interaction. But you can also feel it in the smallness of a moment, a spark of recognition, a stillness under the stars, the realization that being alive inside this vastness is its own form of understanding. When you stand beneath the night sky and feel that strange combination of insignificance and connection, you're sensing something real. It isn't just emotion, it's the direct experience of scale, the mind adjusting to the infinite. That feeling of immensity and quiet is not separate from science, it's part of it. It's what motivates us to learn in the first place. Wonder is the origin of every equation and every telescope. It's the reason we keep building ways to see farther, even knowing that there will always be more beyond reach. In the dark, our eyes find only a fraction of what's there. We see stars, but between them lies more space than we can comprehend. Yet that space isn't empty. It's filled with light we can't detect, particles that rarely interact, and fields that hum quietly in the background. The apparent stillness is full of motion. The apparent void is full of presence. The more precisely we measure it, the more intricate it becomes. What looks simple from afar reveals endless layers when examined closely. The smallest particles behave with the same strangeness as the larger structures. Quantum uncertainty on one end, cosmic expansion on the other. Two mirrors facing each other, each reflecting the other's mystery. And through all of it runs a single thread. The laws of physics, consistent across time and space. The same equations that describe the orbit of a planet describe the bending of light around a black hole. The same principles that govern electrons in an atom also govern the fusion that powers the stars. It's as if the universe is written in one continuous language, with variations in scale, but not in logic. When you realize that, it becomes impossible not to feel reverence. Out of chaos, order emerges. Out of simplicity, complexity grows. Out of vast distances and indifferent forces comes a world that can think, feel, and wonder. That's the quiet paradox at the heart of it all. The universe doesn't need meaning to exist, but it gives rise to beings who create meaning within it. The laws of nature are impersonal, but their outcomes include compassion, curiosity, and love. Out of the same physics that makes stars shine comes consciousness, and with it, the awareness of the stars themselves. When we look outward, we're not just observing, we're completing the loop. The universe that gave rise to minds uses those minds to look back and see itself. Every act of wonder is part of that feedback, the cosmos understanding its own form. When you let that thought settle, the distances begin to feel different. The galaxies, the clusters, the voids, they stop feeling unreachable. They start to feel familiar, like distant relatives instead of strangers. The atoms in those galaxies are kin to the ones in you. The hydrogen in your bloodstream was once free in interstellar space, and before that, part of the primordial gas that filled the early universe. You carry a record of cosmic history within you. Every cell is an archive of stars. Every breath is part of the same cycle that began almost 14 billion years ago. Even time itself, which feels so linear and relentless, begins to take on a new texture when seen from this perspective. The past and future don't vanish. They coexist in patterns of cause and consequence that ripple through the universe. Every photon of light you see began in the past but arrives in the present, connecting you to events across billions of years. Every star you observe is a time capsule. The cosmos isn't something happening out there, it's something unfolding everywhere, including here, in this very moment of awareness. That sense of connection doesn't make the universe smaller. It makes it infinite in a new way, not just spatially, but in depth. Infinity becomes not just about size, but about meaning. You begin to realize that the universe doesn't have to be personal to feel intimate. Its vastness is the same vastness that allows for everything you know and love. If it were smaller, simpler, more predictable, there would be no room for life, no room for complexity, no room for minds capable of reflection. The immensity isn't an obstacle, it's the condition that makes existence possible. When we talk about reaching the edge of the universe, we usually mean the observable limit, the distance light has been able to travel since the beginning. But there's another kind of edge, one that exists not in space but in understanding. It's the point where knowledge turns into silence. Beyond that point, questions remain, waiting to be asked. The edge of wonder isn't a boundary to cross, it's a place to linger. It's where curiosity lives, not in answers, but in the space between them. At this point in human history, our view of the universe is both astonishingly vast and profoundly incomplete. We can describe the evolution of matter from the first seconds after the Big Bang to the formation of galaxies and stars. We can trace the origin of elements, map the cosmic background, and calculate the universe's age with precision. And yet, more than 95% of it remains hidden. Dark matter, dark energy, the nature of space-time itself. The more complete our picture becomes, the more it reveals what's missing. That's not failure, that's progress. The unknown keeps the story alive. There's a kind of serenity in that realization. The universe doesn't demand that we understand it entirely. It allows us to participate at our own scale, to explore within our own limits. Our purpose, if there is one, may not be to solve the cosmos, but to experience it, to notice, to reflect, to be present within its unfolding. Wonder, in that sense, is not a luxury. It's a function of existence. It's how consciousness relates to reality. It's how the universe recognizes itself in the act of awareness. In daily life, it's easy to forget that connection. The cosmos feels far away, hidden behind the routines of living. But even in ordinary moments, a quiet walk at night, the hum of city lights, the warmth of sunlight through a window, the same universe is there, moving through you. Every heartbeat, every breath, every flicker of thought is powered by energy that once belonged to stars. The scale may change, but the source remains the same. To remember that is to see the infinite in the familiar, the cosmic in the personal. And this is where wonder lives, not only in distant galaxies or theoretical horizons, but in moments of awareness. You don't need a telescope to find it. You only need to notice the connection between yourself and everything else. The wonder that holds the stars together is the same wonder that holds you together. It's the gravity of curiosity, the quiet pull that keeps life oriented toward understanding. Sometimes, when scientists talk about the future of the universe, they describe it in terms of entropy, a long decline into darkness, a slow fading of energy until nothing remains but cold, thin radiation. It's a bleak picture on the surface, a vision of cosmic loneliness stretched over infinite time. But there's another way to see it. Entropy is not just decay, it's transformation. It's the process by which energy disperses, complexity emerges, and new structures arise. Even in the farthest future, even in the deepest quiet, the potential for something remains. The same laws that created stars from chaos will continue to shape whatever follows. The universe isn't dying, it's changing. In that way, the story never ends. The edge of wonder is not a conclusion but an ongoing moment. It's the point where knowing and not knowing coexist peacefully. It's where science meets awe, where explanation meets gratitude. It's what allows us to keep asking, even when answers seem unreachable. Wonder isn't fragile. It doesn't fade with knowledge, it deepens. The more we learn, the more astonishing the universe becomes. If you close your eyes and imagine the night sky, the faint starlight, the vastness, the silence, you're participating in the same act that has connected humans across all of history. Every generation has looked up, felt small, and yet somehow larger for having seen the sky. That feeling, that quiet recognition of connection is timeless. It's the moment when the horizon of knowledge meets the horizon of emotion. It's what it means to be alive in a universe like this. So much of what we call understanding is really the art of listening, to light, to matter, to the patterns of nature. The universe speaks in many languages, in the hum of background radiation, in the orbit of planets, in the structure of atoms. We learn to translate those patterns into meaning, and in doing so, we realize that the act of listening is itself a form of harmony. The cosmos doesn't shout its secrets, it whispers them, softly, patiently over billions of years. To hear them requires stillness, And perhaps that's where we find the truest form of knowledge, not in certainty but in attention. To look at the universe and feel wonder is to understand something essential, even if you can't explain it. It's to recognize that existence itself is rare, fragile, and extraordinary. It's to feel, if only for a moment, that you are exactly where you belong, inside something vast and alive, part of a story that began before you and will continue long after. The edge of wonder is not a destination. It's a state of being, the place where knowledge and mystery meet and recognize each other. To reach it is to see that science and awe are not opposites. They are two sides of the same impulse, to see clearly, to feel deeply, to know that something greater exists and that we are part of it. And as the galaxies drift farther apart, as light continues to travel through space, as time stretches quietly onward, wonder remains constant. It doesn't fade with distance. It doesn't weaken with age. It's woven into the structure of the universe, just as it's woven into us. The same energy that drives expansion drives curiosity. The same force that shapes galaxies shapes thought. So, when you look up tonight, whether from a city street or a dark field, whether through clouds or clear air, remember that the light reaching you has crossed unimaginable distances to arrive. It's the same light that filled the early universe, the same energy that gave rise to everything you know. And in this brief moment, you are part of that journey. The universe is looking back through your eyes, recognizing itself in reflection. Here, at the edge of wonder, everything feels connected. The smallest particle and the largest structure, the earliest moment and the present one, the observer and the observed, all parts of one continuous unfolding. The horizon stretches endlessly, but you are already within it. There's no edge to reach, no boundary to cross. There's only this, awareness meeting infinity, silence meeting understanding, light meeting the mind that can see it. And somewhere in that quiet meeting the universe breathes. The same breath moves through galaxies and through you. The same time flows through stars and through thought. And as it all continues, expanding, cooling, evolving, the wonder never leaves. It's always here, waiting, patient as starlight, calm as distance, infinite as space. And now, as the night deepens and the thoughts begin to drift, let the idea of the universe slowly fade from size into feeling. The galaxies, the light, the distances, they're still there, moving silently through time, but you don't have to follow them anymore. You can let them move on their own, as they always have. All that's left is the quiet recognition that you are part of it, that the same calm that fills the stars also fills you. Breathe slowly. Feel the air as it enters and leaves. Somewhere in that rhythm is the pulse of everything, the same slow, patient heartbeat that moves through the cosmos. You don't need to hold it, just notice it. The night sky above you isn't asking for thought now, it's only offering stillness. Every sound around you grows softer, every sense grows lighter. The body rests and the mind for a little while can stop measuring, stop reaching. The universe doesn't need your attention to continue. It simply carries you within it, the way a current carries a leaf. So let yourself drift. Let the galaxies become distant embers, the stars dissolve into darkness, the horizon fade into quiet. The questions can wait. The wonder doesn't end, it just changes shape. From thought into peace, from curiosity into rest. And as you breathe in, the whole universe moves with you. And as you breathe out, it expands quietly, endlessly, all around you. Good night and sleep well. You're home in the universe, always.